welcome everyone to a new video. So in this video we are going to talk about the chapter 31 from the book Clayden, and it is going to be on the saturated heterocyclic and its stereoelectronics. So the first thing that we are going to discuss in this particular chapter is about the saturated nitrogen heterocycles. And it discusses why amines they are basically more nucleophilic. So the kind of saturated heterocycles that we are talking about. So far in the previous chapter we have talked about heterocycles like aromatic heterocycles having heteroatoms, जैसे कि what you have is furan. So in this particular chapter we are going to see heterocycles without any aromatic ring, जैसे कि the 5-membered heterocycle having NH is called pyrrolidine, and if it is 6-membered, this is piperidine, and this is piperidine, and this is morpholine. So in exam you could be asked various type of question. For example, arrange these four in the increasing order of their basicity, or you could be asked, let us suppose if I ask you out of piperidine, piperidine and morpholine, which one is more basic. So all these things we are going to discuss in this particular chapter, in fact in this video. So let's jump into it. So the first thing in the chapter they are discussing is, they are saying secondary amines. So here what we have is secondary cyclic amines, or should I say secondary cyclic amines. They are basic. Obviously they have these lone pair of electrons on nitrogen, right? As a result of which they have this basic character. Apart from that, they are also nucleophilic in nature, okay, because of this lone pair of electrons. And you will see a lot of drugs in pharmaceutical industries which have these saturated heterocyclic cores attached in it, okay. Let us suppose, for example, if we have this molecule, we are carrying out the acylation. In fact, amide bond formation by acylation. So we treat it with the base. So this is what is happening. It attacks the carbonate. It comes back, and the chloro leaves. So what we get is a drug called trimetrozine, which is nothing but a tranquilizer or muscle relaxant. Okay. So that is a drug which can be made by a acylation reaction, and we can see what it has is this saturated heterocyclic core in it. Apart from that, if we start from diphenylbenzyl chloride, and in the reaction we know what happens, the chloro it's released, as a result of which this secondary carbocation is generated. Now if we treat it with this N-methyl piperidine product, then what it does, this attacks to give you cyclazine. Cyclazine is also a drug which people use for travel sickness. You must have seen a lot of people when they travel they feel sick. So this is a drug that is usually given to them to make them feel better during the travel sequence. So here we're just talking about just looking at the utility of these utility of these saturated heterocycles. That's what we are looking here. Now, apart from that, if we have seen, especially अगर हम देखें the chemistry of pyrrolidine and piperidine, we have seen that, or in fact even morpholine, they undergo one of the reaction which is a characteristic of the cyclic secondary amine, which is the enamine formation. So here what we are forming is the enamine. It is one of the characteristic reactions of these cyclic amine. In fact, you have an aldehyde here, or you could have also had the ketone. Apart from the aldehyde, ketone also, both of them they undergo the reaction. So here what happens, it attacks, protonation, lone pair of electron, they come, they release. So this is what we have is an imine. So this proton comes here, as a result of which we form is an enamine. Now, the enamines that you form with pyrrolidine, for example, this pyrrolidine or piperidine, they are more stable as compared to the enamine that you form with the acyclic amine. Let us suppose if you are forming an enamine using diethylamine and you are forming an enamine with pyrrolidine. So the enamine with the pyrrolidine, it is going to be more stable than this one. So what do I mean by that? I mean that this is this type of. So it is this one which is going to be more stable than this sort of enamine. उसका reason क्या है? उसका reason ये है कि pyrrolidine and piperidine they are more basic and more nucleophilic as compared to the डाइथैलामीन. ठीक है, अगर हम दोनों की बेसिसिटी कंपेयर करें तो दोनों में हार्डली कोई डिफरेंस होगा. बट व्हाट इज द रीजन? उसका रीजन ये होता है कि बट यू हैव दिस these alkyl groups. अगर आप इस चेन के अंदर देखें, these alkyl groups they are held back. मतलब ये क्योंकि रिंग के साथ एसोसिएटेड है यहाँ पर, ठीक है, रिंग में बंधे होने की वजह से, because they are within the ring, as a result of which these alkyl groups they are tied back. मतलब उनके हाथ पीछे बांध दिए गए हैं. As a result of which these lone pair of electrons they are easily available. They are easily available for to attack. Whereas in the case of alkyl group, अगर पास alkyl group होता है, हमको पता है they are free to move, they just move in various directions, as a result of which these lone pair of electrons are less available to attack. So that is the reason why you will see the enamines from pyrrolidine and piperidine are more stable as compared to, if you compare to the cyclic amine. ठीक है? So in a way, अगर हम ऐसा भी बोल सकते हैं, cyclic amines are more stable than or more basic than the acyclic amines. ठीक है? Acyclic amines है. So that is one of the reason, because their hands are tied up, or alkyl groups are tied at the back, and lone pair of electrons are easily available. Now we are going to look at the reactivity of these amines that have been discussed. कि acyclic amine versus cyclic amine, उनकी reactivity देखते हैं और basicity से compare करते हैं कि क्या कुछ फर्क है कि नहीं. That is what has been discussed in the chapter now. Let's look at that. So as I said कि हम दोबारा से देखेंगे. Now we are going to look at the reactivity pattern. Let us suppose what we have is this trialkyl amine and we are carrying out a reaction with methyl iodide. ठीक है? So obviously lone pair of electron nitrogen, they are attacking on the methyl, resulting in the form of this quaternary salt. अब अगर हम इस रिएक्शन का रेट अगर हम स्टडी करें, so let us suppose when this amine is triethylamine, अगर ये हमारा triethylamine है, ठीक है, if the reaction rate is 1, और अगर हम इसकी जगह if we use quinnuclidine, the rate of the reaction is 63. Obviously these are the relative rate of reaction. अगर इसका 1 है तो this is 63. So there is an almost 60-fold increase in the rate of the reaction अगर आप क्या कर रहे हैं when you are using a cyclic amine versus acyclic amine. लेकिन अगर हम उसकी बेसिसिटी देखें, अगर हम pK देखें, pK दोनों की दोनों almost same है. This is almost 10.7, this is 11. So there is hardly any change in the pK whereas the reactivity is high. So what is the reason for that? उसका reason जैसे कि मैंने पहले भी बोला कि here the alkyl group, they are tied back, as a result of which these lone pair of electron or nitrogen, they are more available, they can easily attack. Whereas in the case of triethylamine, what you have is these freely moving alkyl chain, as a result of which these are not as easily available. और सिमिलरली अगर आप यहां पर भी देखेंगे डेको की रिएक्टिविटी स्लाइटली कम है, बट अगर हम इससे कंपेयर करें, स्टिल इट इज 40-fold increase in the rate of the reaction. So this is also cyclic amine. Okay, now this is what I want to do. Now what about the basicity? अब देखिए क्या यहां पर क्या है, क्योंकि हमने क्या किया pK of NH+, that is how we calculate. I just here what these lone pair of electron need is a proton. प्रोटॉन हमारा क्या होता है, इतना स्मॉल है. दिस इज सच अ स्मॉल, प्रोटॉन इज सो स्मॉल दैट इट डजंट रियली केयर अबाउट द स्टीरियोइक्स एंड ऑल. एज अ रिजल्ट ऑफ व्हिच देयर इज हार्डली एनी डिफरेंस बिटवीन द बेसिसिटी. प्रोटॉन आपका इतना स्मॉल है, उसको फर्क नहीं पड़ेगा कि चेन कितनी बड़ी है कितनी छोटी है, वो यहां पर भी आसानी से आ जाएगा और यहां पर भी आसानी से आ जाएगा. दैट इज द रीजन व्हाई द पीके ऑफ दीज टू देयर इज हार्डली एनी डिफरेंस. हाउएवर रिएक्शन के रेट की तब बात करते हैं, वहां पर अगर कोई रिएक्शन करा रहे हैं, वहां पे लोन पेयर ऑफ इलेक्ट्रॉन्स की अवेलेबिलिटी इंपॉर्टेंट हो जाती है. व्हाई? बिकॉज वी आर ट्रीटिंग इट विद वी वांट टू इंट्रोड्यूस सर्टेन फंक्शनल ग्रुप्स व्हिच हैज लार्जर स्टीरियोइक्स, whereas for the proton it is barely very small. So here the stereoics, they do not play any role. ठीक है? Now here is the basicity order of some of the amines. जैसे कि similarly here if we look at the diethylamine and this piperidine, the basicity are very similar. Here what we have is a dibutylamine with, I mean इनकी यहाँ पर दिखाने का मैंने मकसद यही किया है कि if you just look at their basicity, they are pretty similar. Now एक जो बहुत दूसरी important चीज है, if you compare the pKa of, ठीक है, if you compare the pKa of quinnuclidine which is 11.3 वर्सेस डेप्को की आपकी दो पीके हैं. क्यों? क्योंकि एक दो नाइट्रोजन है, दोनों के दोनों प्रोटोनेट हो सकते हैं. सो दिस इज द पीके ऑफ सेकंड प्रोटोनेटेड नाइट्रोजन. नाउ क्विनन्यूक्लिडिन की आपकी क्या है, 11 है पीके, ठीक है, ऑफ इसके प्रोटोनेटेड एमीन की. ठीक है, ऑलवेज रिमेंबर दैट. नाउ डेप्को की आपकी 8.8 है, मतलब it has reduced. It means that quinnuclidine is more basic than the dapco. Similarly, in the case of piperidine, अगर देखें, as soon as you introduce a heteroatom at this position, so when you have introduced oxygen, you have 8.4. When you have introduced nitrogen, you have 9.8. ठीक है, उसका रीजन क्या? What is the reason for that? ठीक है, जैसे ही as soon as you introduce a heteroatom into the ring, जैसे आपने heteroatom ring में introduce किया, so what happens? due to the inductive effect of these heteroatoms, क्योंकि हमें पता ऑक्सीजन is electronegative in nature, as a result of which what it does, they tend to withdraw the electron density from the chain. अगर वो electron withdrawing, if they are withdrawing the electron density from the chain, so it means that these electrons are now going in this direction. As a result of which, the lone pair of electron and nitrogens, they are more involved into the ring system and less available. That is the reason why you can see the basicity of these amines is less if you compare to the normal cyclic amine. यहाँ पर भी आपका वही हो रहा है. So you have an additional heteroatom nitrogen here, as a result of which the basicity is reduced. ठीक है? It is pretty clear because of the inductive effect. Now we are going to look at कि किस तरह से आपका जब let us suppose why these two values are different. वो किस वजह से होता है कि एक तो आपकी जैसे कि मैंने बोला once you have an extra NH here in the piperidine molecule में या फिर डेप्को के अंदर, why the second value is even less, उसको हम देखने की कोशिश करेंगे. बट उससे पहले हम देख लेते हैं कि what happens, what makes, if we look at the morpholine is a very useful base. It's a very useful base in the organic chemistry. उसका रीजन क्या है? If we look at the pK of it, ठीक है, it is 8.4. This is less basic than triethylamine. Triethylamine की pK देखिए तो हम क्या 10.7. So this is less basic than the triethylamine, but this is more basic than the pyridine. So एक तरह से this is falling in between these two bases. So there are a lot of times when morpholine has been used as a very efficient base to carry out organic transformation. अगर आपने गिवार्ड रिएक्शन देखा है या अगर आपने बहुत सारे मॉलिक्यूलर आर्किटेक्चर देखे हैं, so this behaves as a very useful base in many reactions. ठीक है? Now let's look at the other things that have been discussed in the chapter. Now coming back to the fact that why the pK of the diamine is lower. Why do they have the lower pK? Second pK. ठीक है? जैसे कि for example in the case of DAPCO, the first one is 8.8, the second is 3. In the case of piperidine, it is 9.8 and 5.7. So, what happens as soon as one of the nitrogen it becomes protonated? As soon as it becomes protonated, this has nitrogen has now become electron deficient. So, this is deficient of electrons. As a result of which, it withdraws the electron density from the ring more efficiently than the unprotonated one. That is the reason why this value is much lower as compared to the normal one. So this is something that you should understand and remember, because there could be a question where you could be given such protonated amines and you could be asked to arrange them in the order of their basicities. Okay, so that's where you should remember these concepts. Now they have also discussed about the at times हमको पता है this is the structure of the LDA. LDA is usually not a bulky base. ठीक है? We still have a hydrogen here. Apart from that, we can use other bulky bases like TMP. This is the structure of TMP. So around nitrogen, what you have is the two methyl groups and one alkyl chain. So this is pretty bulky group. And when you treat it with the butyl lithium, what you generate is a lithium TMP. So this is a base that is used in many reactions when you need a lot of bulk around the reaction and when you want to selectively form the kinetically controlled enolates. ठीक है? बिना किसी side reaction के. So that is where they are used. Now coming back to the named reaction that has been discussed in the chapter, which is Baylis-Hilmann reaction. In fact, this is one of the reactions that was observed when you treat an aldehyde with ethyl acrylate in presence of DAPCO. Nowadays, a lot of variants of this particular reactions are known, but in this chapter, only this example has been discussed. So, the mechanism is pretty straightforward. So, what is happening? This carbon and this carbon. It is this carbon and this carbon. We are forming a new carbon-carbon bond. So, which is an interesting reaction. But if we look at the reaction, the original protocol takes 7 days. So, it means it's a very slow reaction and it proceeds under thermodynamically controlled conditions. So, the first step is pretty straightforward. So what is happening? As I said, the lone pair of electron on nitrogen, since these alkyl group are tied back, so what it does, it attacks this in a conjugate manner. So that's a conjugate manner. This attack is taking place. So the next step is what is happening. So what you have an aldehyde. So there is an aldol condensation that is taking place in this particular reaction. So once this is formed, it comes here, it moves here, and this is formed. So once this comes, it moves here and the DEPCO is released, and what you get is a desired product. So this is a very, very important reaction if you want to form this carbon-carbon bond. And one thing you should remember here, the elimination, it proceeds via even CP elimination. So this is something that you should remember, because at times you could be given this reaction sequence, आपको reaction sequence दिखाया जा सकता है, and you could be asked what is the elimination mechanism via which this reaction is proceeding. So you should remember it is even CP. Okay, so this is pretty much about this one. So now in the chapter they are discussing the chemistry of the aziridines. So these aziridines are 3-membered heterocycles, and if we have the 4-membered ring having an NH group, it is called azitidine. So what it says that such rings can be easily opened. Okay, because you have the C-member thing, they are prone to opening under the desired conditions. Just like for example, what we have is an acid chloride, and if we carry out the reaction with aziridine, ये spray आपका करेगा, but it will do attack, this will go, this will come back, and that chloride leave. But the issue is that this particular intermediate, this is not stable. ये आपका intermediate stable नहीं है. So what happens, जो आपका chloride आपका reaction में से निकला है, what it does, it behaves like a nucleophile, as a result of which what it does attack, and this ring opening takes place, and what you get is this particular product, which is the amide coupling having a chloro in 95% yield. So this is the only major side product. Let us suppose if you want to make the N-acetyl aziridine, what is something that you can do? So basically you can carry out this reaction in presence of a base. So base क्या करता है कि as soon as you have this intermediate forming, so base is going to abstract this proton, as a result of which you can easily isolate this N-acetyl aziridine, and this is very stable. You can easily do that. Apart from that, अगर हम reaction देखें aziridine की, let us suppose what we have is this benzyl chloride in presence of a base. Again देख सकते हैं, अगर base की presence में हो रहा है तो इसका clearly मतलब है कि it is stable. Okay, it is stable. If this is happening in presence of the base, it means there is something to get rid of to make sure that this proton can be taken away from the nitrogen. Now, this is exactly what is happening. The lone pair of electron they are attacking. The chloro is released. So the chloro आपका क्या है, chloro counter anion यहाँ पर है. But what we have is this potassium carbonate base in the reaction. So what this base does, this subtract this proton. As a result of which, now what you have is this aziridine moiety within the molecule. So आपने replacement के बाद. So what you are doing is basically, then you are introducing a benzyl bromide into the reaction. So जैसे कि हमने बोला था कि these lone pair of electron on nitrogen, they are pretty nucleophilic. और जैसे मैंने बोला भी है कि ring system के अंदर क्या होता है, because these alkyl chain, they are tied back, so these are pretty available to attack. This is exactly what happens. They attack the benzyl bromide, so bromo is released. So what you form is this intermediate. Now in this reaction, to carry out this particular transformation, we can see they have not used any base. So what is happening, as soon as this intermediate is formed, it is attacking this carbon, releasing the ring strain. So in पूरे processes में यहाँ पर भी आपका क्या है, it is a release of the ring strain. So what you are getting is the formation of such interesting compounds. So what सबसे interesting बात इस compound की क्या, you can clearly see nitrogen on one side you have a different aryl group, on the other side you have a different aryl group, and here what you have an alkyl group. So you can make variety of tri-alkyl amines using such elegant method utilizing aziridine chemistry. Now we are going to look at the basicity. अगर हम aziridine की basicity compare करें other heterocycles से, जो higher sized ring है, क्या ये ज़्यादा basic है, क्या less basic है? And if they are less basic, what is the reason for that? That is something that we are going to look at now. So basically, in the case of the aziridine, they are less basic than pyrrolidine or piperidine. अगर हम इसकी basicity देखें, ठीक है, this is the pK of the protonation. Now I just want to clarify one confusion. I guess I don't know if the students have. Usually क्या होता है कि whenever we are dealing with the acid, let us suppose if I am dealing with HCl, ठीक है, or if I am dealing with H2SO4, here what we have is this proton, right? So there we can easily use pK. Usually for bases, usually for the bases, what do we look at is the pKb of the base. और अगर हमको if we want to compare the bases, ठीक है, अगर हमको बेस को कंपेयर करना है in terms of pKa, so what do we usually do? ठीक है, we usually take the pK of the protonation. So इसका मतलब क्या है कि this is what we take, ठीक है, यहां पर इसको ये समझ के चलिए, this is what we are measuring, this is the pK we are measuring, that how acidic this is. right? That is what pK of protonation means. So don't get confused. Usually we use pKb as well. अगर हम पूरा का पूरा basis consider करें, we can use pKb as well. There is no problem. But if you want to compare bases in terms of pK value, it is the protonated, ठीक है, pK that we compare, that how easily it can just get rid of this hydrogen. ठीक है, ये कितनी आसानी से अपना प्रोटॉन दे सकता है, not hydrogen. Why do I keep saying hydrogen? How easily it can give up this proton. ठीक है, that is why it is pK of protonation. Now, if we look at the pK of aziridine, it is 8. And if we compare this pK with the compound, here what we have is the benzophenone imine. ठीक है, benzophenone का हमारा imine है, which has a pK 7.2. So इसकी pK is very close to a compound in which nitrogen is sp2 hybridized. Here this nitrogen is sp2 hybridized. So इसका मतलब क्या है? What does this mean? It means that the lone pair of electron, this nitrogen, ठीक है, they are in an orbital which has more s character. ठीक है, और वैसे भी हमको पता है which has a more s character, and we know in the case of the three-membered ring, usually this is the property of a three-membered ring, because once these carbon-carbon bonds are formed, the orbitals are bent orbitals, as a result of which these lone pair of electrons, they acquire more s character, जिसकी वजह से they are less available. That is the reason why these are less basic as compared to the pyrrolidine or the piperidine. Now, एक interesting case देख लेते हैं, which could be asked to you in terms of the IR value. You could be given 3-membered, 4-membered, 5-membered, and you could be asked to arrange in their increasing value of their carbonyl stretching frequency. So this is a very good example. Here what we have is an anion dimethyl acetyl group, ठीक है, acetyl group, anion dimethyl formamide. That's what we have. In this case, what is happening? These lone pair of electrons, they come undergo conjugation, because आपका जो नाइट्रोजन के लोन पेयर ऑफ इलेक्ट्रॉन है, here what you have is a planar nitrogen. Planar nitrogen होने की वजह से it can undergo conjugation with this carbonyl. ठीक है, that is the reason why here the stretching frequency that you see is 1655, which is very typical of an amide. But in the case of when you have this cyclopropane ring, aziridine ring attached to the carbonyl, unfortunately what is happening, because these lone pair of electrons have more of a s character, इसका ज्यादा s character होता है, so here this nitrogen is pyramidal होने की वजह से the planar in which what you have used this carbonyl is and the plane in which this lone pair of electron is, इनके बीच में there is a very poor overlap, there is a very poor interaction, you can say poor interaction or poor overlap, जिसकी वजह से as a result of which this carbonyl behaves more like a normal carbonyl. That is the reason why you can see the stretching frequency of this carbonyl is 1702, which is typical of ketones because of the reasons that I explained here. Okay, so this is very, very important data or the details that you should be aware of. So now we are going to look at the oxygen heterocycles. So just like the nitrogen heterocycles, the ring opening is one of the characteristic of these oxygen heterocycles. जैसे कि 3-member is oxidane, 4-member is oxidane, and then you have tetrahydrofuran and then tetrahydropyran. So as the ring increases. Now, let us suppose if you are carrying out the reaction of oxidane with n-butyl lithium and BF3 etherate, it usually undergoes ring opening. Like if you do not add this Lewis acid, ठीक है, because you need to activate the ring. Suppose if you are carrying out the reaction of n-butyl lithium with oxidane, there is no reaction. You do not observe any reaction without the Lewis acid. So what the Lewis acid does, it interacts with the lone pair of electron on the oxygen, जिसकी वजह से it becomes protonated. Now it is withdrawing the electron density from the carbon, जिसकी वजह से it is forcing this ring to be open. So आपका जो butyl lithium में होता है, it attacks, as a result of which ring opens. After the workup, what you get is the quantitative formation of 1, 2, 3, 4, 5, 6, 7 heptanol. ठीक है, what you get is the quantitative formation of this product. Let us suppose if you carry out the same reaction with THF के साथ अगर आप करते हैं butyl lithium, Lewis acid, again you need it. But in this case, what you get is the octanol, but the yield is pretty low. It is not significant. ठीक है, इसका मतलब है कि जैसे आपका रिंग बढ़ रहा है, वैसे वैसे इसकी ये जो unwanted reaction कह लीजिए, unwanted ring opening कह लीजिए, its tendency is usually reducing. Now, usually you know that most of the reactions of butyl lithium when we carry out in using the solvent THF या फिर ether, उसको हम यूज करते हैं. उसका रीजन क्या होता है कि कोऑर्डिनेटिंग एबिलिटी की वजह से. नाउ One of the unwanted reactions of THF or butyl lithium जो कि देखा जाता है is the deprotonation one, and usually mostly when we carry out the reaction of butyl lithium, it is usually at negative temperature, -20, -78, -50, to make sure that there is no unwanted reaction takes place. But let us suppose if you are carrying out a reaction at 0 degrees Celsius, so this is one of the unwanted deprotonation reactions takes place. So what happens? So the lone pair of electrons of nitrogen, they coordinate with the lithium. Okay? So this is what I am saying, at 0 degrees Celsius, this protonation is taking place. As a result of which, now this butyl group, it is negatively charged, this abstract this proton to lead to the formation of this particular lithium anion, carbanion. So what happens? This carbanion then undergoes reverse 2,3 cycloid 2 plus 3 cycloaddition. So these lone pair of electrons, they come here, this bond moves here and it leaves here. Okay? So you can clearly see what you are forming. You are generating an ethylene gas into the reaction. क्योंकि ये gas है, it just escapes out of the reaction. And what you are generating is an enolate. So this enolate usually क्या होता है? It reacts with itself to polymerize. ठीक है? So it ends up being polymerized. So sometimes in the reaction you do see such polymerized product, but these unwanted reactions at times आपके जो compound होती है उससे they react with your compound, and so while let us suppose if you are doing a reaction on a pharmaceutical industry or a big scale, you need to take care of all these side reactions that are taking place in order to identify the impurities that are forming in the reaction. So here one of the unwanted reaction that is taking place via the deprotonation. इसका एक famous example है. Let us, when they carry out the reaction of, let us suppose what we have is this compound in butyl lithium THF. ठीक है? So what is happening? The butyl lithium is abstracting this proton. So what they were observing is this impurity. Here what we have is an ethyl group, and they were not able to understand from where this ethyl group is coming. So then they realize what is actually happening. Something like this is happening, and what you are generating is an ethylene gas. So this lithium ionate, it was attacking the ethylene gas to generate the ethyl group, or to put the ethyl group at this particular position. So sometimes you need to take into consideration a lot of other things that are happening into the reaction. So now while discussing the sulfur heterocycles, they have rather discussed the example of diethyne chemistry. So here what we have is the diethyne, and we clearly know this hydrogen which is next to both the sulfur group, it is pretty acidic in nature. So when you add a base, what you generate is a carbanion. So they have combined the oxygen heterocycles and diethyne chemistry just to give us a very, very elegant approach to form this compound, such compounds. And this is a very, very important example. So here what we have is an oxygen heterocycle, saturated oxygen heterocycle. Here N can be 0, 1, 2, 3. So depending upon the number of carbons, it can be oxidane, it can be oxetane, it can be tetrahydrofuran, it can be tetrahydropyran. हमको पता है, we clearly know these oxidane rings, they do not open as such. इनको activate करना पड़ेगा. So how do we activate it? With the presence of the Lewis acid. This is exactly what we did. They separately added the Lewis acid to activate the oxygen heterocycle. So now what is happening? Now this is going to go attack and open the ring. So this is what you form. So the last step is mercury catalyzed deprotection of diethyne to give you the keto compound. So such example could be very, very important, and I think this could be asked in, I think, IIT JAM exam. So yeah, so this is pretty much about the sulfur heterocycle that they have discussed in this chapter. See, now in the chapter we are going to talk about the conformation of saturated heterocycles. Okay? So before going into the conformation of the saturated heterocycle, let's look at how we can use NMR. Just few of the examples that have been discussed in the book. So how we can use the NMR to understand the conformation. So जैसे कि I have already made a video on the dihedral angle, that is a torsion strain के ऊपर I have made a video in which I have explained a lot of terms that we used in chemistry, like synclinal, antiperiplanar, and all those type of terms that you hear nowadays और कभी एग्जाम के अंदर. And when you hear those words, what does it really mean? Okay, so that is something that I have been discussed. You can watch that video on the torsion strain. Now, what do they mean by that? So use of NMR to study conformation. So there was a relationship that was established by the Karplus, which explained if there is a certain angle between two bonds, what could be the coupling constant between the hydrogen. Okay, that is exactly what we are going to look at. For example, when these two hydrogens, here they are where? They are axial position, okay, and the dihedral angle between them is 180 degree. When the dihedral angle between them is 180 degree, their coupling constant is usually 10 to 12 Hertz. Here 3H means is these two hydrogens are 3 bond away. For example, this is 1, this is 2, this is 3. Okay, that is what this 3 means, just in case if you don't know. Okay, so these are 3 bonds away. And when this dihedral angle between these two, here in this case when it is axial equatorial, okay, axial equatorial hydrogen, the dihedral angle is 60 degrees, this coupling constant comes to 3 to 5 Hertz. Similarly, when both of them are equatorial, still the dihedral angle between both of them becomes 60 degree and the coupling constant is 2 to 3. So this, when both of them are equatorial to each other, this is slightly less than the axial equatorial. Although in these two cases it is, we look at the other factors to distinguish whether we have axial equatorial. Just in case if we discuss the example, we are going to look into that. Now let us talk about this bicyclic system. So here, this dihedral angle, so the angle between this hydrogen and this hydrogen, if you look at it is 90 degree. And when the angle between them is 90 degree, there is barely any coupling observed between these two protons. So what do you observe? Coupling constant is 0. So all this has been expressed in the form of a relationship where what do? You make a relationship between the coupling constant versus dihedral angle, so which is called the Karplus relationship. Now if you look at here, you can clearly see when the dihedral angle is 0, this is going to be the coupling constant, whatever value. Here you can just write the certain values. Let us say you just write it as 10. And as the dihedral angle is decreasing, so for example here it could be 45 degrees, you can clearly see the coupling constant is also reducing, and as the dihedral angle increases from 90 to 180, the dihedral angle is going to, the coupling constant becomes more. But you should always remember this thing, when the dihedral angle is 0 degrees, okay, when the dihedral angle is 0 degree, for example in the case of the eclipse conformation, let us suppose if I give you this example, here methyl, OH, let us just type OH, and here just type bromo, okay. And if I just draw the Newman conformation of this one, then I will know that these two hydrogens, the dihedral angle between, in this conformation, ठीक है, इसके बहुत सारे conformation हो सकते हैं, in this particular conformation, the dihedral angle between this and this hydrogen, this is 0 degrees, so it means its coupling constant is going to have some value like 10. And whenever they are trans to each other, that is when the dihedral angle is 180 degree, the coupling constant is also going to become like 14 somewhere around. So remember, when it is 180 degree, it is more than when it is 0 degree. Just keep that particular thing in mind. Now we are going to look at some of the examples, how such relationship, how the coupling constant can be used to interpret the conformations in the case of the heterocycles. That's what we are going to look at. So now we are going to look at this particular interesting problem. So here what we have is 4-tetrabutyl cyclohexanone. If we carry out the reduction of cyclohexanone, then it can give us, there are two products possible. Of course, the hydride can attack from the top phase, it can attack from the bottom phase. So we can have OH group at equatorial position or OH group at the axial position. And this can be simultaneously written as this one. So let us suppose in this case, how they can ask you a question. It could be very interesting. They can tell you that, okay, so what we have is this 4-tetrabutyl ketone. Let us suppose they might ask you that we have this one. We have this 4-tetrabutyl cyclohexanone, and we are carrying out a reduction, and the product that we are getting is this one. They are not going to show you the stereochemistry of OH or this hydrogen or the hydrogens next to each other. They are going to show it like zigzag bonds, and they are going to give you the coupling constant. For example, they are going to give you, let's say, the coupling between HA and HB is XYZ, and the coupling between HA and HC is XYZ. So based on that, predict which is the major product that is formed in the reaction. So they are going to give you the coupling constant values, and they might give you the NMR values as well. So it is those how on the basis of the coupling constant you can predict the exact product that is formed. We are going to look at that. For example, in this case, when the attack is taking place from the axial position, so here what we have is an axial attack, here what we have is an equatorial attack. So the axial attack is going to give us this one. So here the HA is at the axial position, ठीक है? And इससे भी हम देख सकते हैं और इससे भी हम देख सकते हैं, ठीक है? दोनों का both of them are same, ठीक है? They are symmetric. As a result of which, if we look at the dihedral angle between HA and HC, the dihedral angle between HA and HC is 180 degree. And what we have studied as per the Karplus relationship, whenever the dihedral angle between two groups is 180 degree, usually the coupling constant values are like from 10 to 12 or 13, 14. Okay, here what we are getting the value is 11. Okay, and the dihedral angle between HA and HB is 60 degrees, and from what we have studied, it is going to be somewhere between 3 to 4. So this is exactly what we observe, 4.3. So on the basis of this coupling constant data, I can clearly predict that this hydrogen has to be axial. It is this product that is formed. So it is this product which is the major product on the basis of the coupling constant. Let us suppose if they give you this particular value, where they are going to give you the coupling constant data of coupling between HA and HC and HA and HB, we can clearly see the dihedral angle between HA, HB and HA, HC is 60 degrees. And what we have studied that for that the coupling constant is going to be within that range. In this case, हमको कोई भी बड़ा coupling constant नजर नहीं आ रहा. We are not seeing any value which is like 10, 11, 12. So we can clearly say that this hydrogen is not present at the axial position. So the dihedral angle between the hydrogen and it is coupling to the other hydrogen is not 180 degree. And one of the reasons that I clearly said why this particular conformation is kind of a freezed, the reason being is the presence of the tertiary butyl group. अगर यहाँ पे tertiary butyl group नहीं होता, then you will not get any selectivity, right? You will get the mixture of both of them. It is just the tertiary butyl group which freezes this conformation to give you one product selectively. So that is what we have seen on the basis of the NMR values and on the basis of the coupling constant values, and from what we have studied from the Karplus relationship, we can determine the exact major product that is formed in the reaction. Now we are going to look at one more interesting examples of this. So here we have discussed yet another very important example. So here what they are starting from is an unsaturated acetal. Okay, so this is what we have. This is an acetal which is unsaturated, having a double bond here. So what they are basically doing, they are reducing this double bond using hydrogen and red nickel. So what we can have is two type of acetal forming. If this is getting reduces, we are generating it's not a chiral center actually. So in this particular case, what you get is predominant formation of one of the diastereomers. That's what they observe. So you can either have a cis saturated acetal or trans. Okay, so here what you have is methyl and these two are cis, or we can say both the hydrogens are coming towards us, and here they are away from each other. Now they recorded the NMR values, they had the NMR data. On the basis of the NMR data, they came up with the conclusion that what they get is a cis saturated acetal, and we are going to look at the NMR of the cis one. So how did they conclude that? If we draw the chair conformation of this one, we can clearly see that methyl group and these two are going away from each other. And if we draw the chair conformation, and if we look at from the top, we can see these two hydrogens, they are coming towards us, and methyl and ethyl, they are going away from us. I really hope that you guys have the molecular model, so it will really help you to understand that better. So what they observed was, for this particular hydrogen which is at axial position, they did observe a doublet of quadrat for one proton at 3.92, and the coupling constant was 9 and 6.5 Hertz. So basically, you see the value that we have is 9 and 6.5. So the dihedral angle between this hydrogen and this hydrogen, it is 180 degrees. So that higher value that we are getting is 9, it is because of that coupling. And between this axial and equatorial, it is 60. So the value is slightly higher than for the 60 degree, but still it is within that range. And now if we talk about this particular hydrogen, so here what they are observing is again doublet at 4.4, the coupling constant is 9, and 2. So this is exactly what they are observing. So this higher coupling is because of the coupling between this axial hydrogen and this axial hydrogen. The dihedral angle between them is the 180 degree. And this lower value, which is 2, it is because of this hydrogen and this equatorial hydrogen. So on the basis of that information, they were able to conclude that what they are getting is the cis-saturated acetal. But what is an interesting fact? What they found is when they expose this, when they take the compound ethanol, acidic ethanol, what they end up getting is the formation of the trans compound. So this could be a very important question that could be asked to you. You could be asked that we are taking this unsaturated aldehyde and subjecting it to Reninikel. This is what they are going to show you, one. And the second step they are going to give you is like ethanol, acidic ethanol, or they are going to show ethanol H+. So in the book, they have not explained it in this manner. They have explained this on, they have mentioned this in the lines, as you say, reading in between the lines, where they mentioned when they expose this cis-saturated acetal to acidic ethanol, what they get is the trans product. So you must understand it. Now, in the case of the trans, we can clearly see that one of the hydrogens is coming towards us, the other is going away from us. So if we draw the chain structure, and if we look from the top, we can clearly see this is coming towards us and this is going away from us. Okay. The only difference is now this time the OET group is at the axial position. So what they observe, the value of this hydrogen is very much same to what they observed in this particular case, because this is very similar. And when this hydrogen, this becomes equatorial, since as I said that the coupling constant between this hydrogen and this hydrogen, and this hydrogen, the angle is less. So the coupling constant, they do not get like a very big coupling constant. What they observe is a very small coupling constant. In fact, they observe this particular proton at 5.29. Although if we compare from other two values, this is very de-shielded. This is pretty de-shielded. But the signal for this hydrogen is not well resolved. It is not resolved. That is the reason why they do not mention any value for this particular hydrogen. Okay. So that is how on the basis of the coupling constant, and by if we have the knowledge of Karplus relationship, that how the dihedral angle, how by the variation of dihedral angle the coupling constant varies. So this is exactly what we can implement and come up with the right answer. Now here, because the coupling constant of 6-membered heterocyclic is well defined, so that is why sometimes to assign the stereochemistry of these hydrogen, let us suppose if I have to assign the stereochemistry of these two hydrogen, what do we end up doing? We form the 6-membered heterocyclic. Kyunki whether these two hydrogen they end up being cis or they end up being trans, this can be easily determined because these hydrogens when they interact, they have definite J values. So forming 6-membered heterocycle can be really helpful. For example, here once we have 1,3-diol, we carry out the reaction with benzaldehyde, it presents of an acidic condition. क्या मिलता है हमको? What do we get is a benzalidine acetals. So this is what we form, benzalidine acetal. Now, what is going to be the stereochemistry of this one? That is what we are going to look in these two examples. And acetal formation, whenever we carry out acetal formation, especially the benzalidine acetal, whenever you are dealing with, let us suppose, paramethoxy benzaldehyde or even benzaldehyde, these acetal formations happen under thermodynamic control. So what does that mean? It means that the most stable conformation is formed. As a result of which, once the structures are formed, we can assign the stereochemistry. Suppose here what we have is a 1,3-diol and here 1,3-OH, they are sent to each other. When we carry out the reaction with benzaldehyde under acidic condition, this is the benzalidine acetal we form, where both R1 and R2 are equatorial and phenyl group also occupies the equatorial position. It does not prefer to be at the axial क्योंकि उसका स्टेन होगा. Now, अगर मैंने इसको इस स्ट्रक्चर में कैसे कन्वर्ट किया? If I can just simply look from the top, अगर मैं ऊपर से क्लियरली देखूं, I can see that hydrogen is going behind the plane. It is going below the plane. So the phenyl is coming out of the plane. और इन दोनों की स्टीरियोकेमिस्ट्री ये कैसे है मैं आपको दिखा देता हूं. बट फिलहाल देख लीजिए, अगर ऊपर से मैं देखूंगा दोनों के दोनों हाइड्रोजन क्या है, एक्सियल है. They are behind the plane. And these R2, R1 and R2 they are coming out of the plane. इसको इस कन्फॉर्मर में कन्वर्ट करना बहुत आसान है. सिंपली यहां पर क्या करना है आपको, इसको मैं शॉहर्स कन्फॉर्मेशन लिख सकता हूं. सो यहां पर हमारा प्लेन कौन सा प्लेन है हमारा, दिस इज द एंटायर प्लेन दैट वी आर टॉकिंग अबाउट, राइट. अगर और ये वाला ग्रुप क्या है, OH इज कमिंग आउट ऑफ द प्लेन, हाइड्रोजन इज गोइंग बिहाइंड द प्लेन, दैट इज व्हाट इट इज. अगर मैं इसको सिंपली इस तरह से लिख दूं, R1 R1 and hydrogen is going behind the plane, OH is coming out of the plane, और इस सेंट्रल कार्बन को मैंने X से रिप्रेजेंट कर दिया, and this is R2 hydrogen OH. सिंपली मैंने क्या किया है, I have brought about the rotation around the single bond. अब मैं OH को अकॉर्डिंग चाहता हूं कि I want to bring OH into the same plane. So what I am going to do, I am going to move this side, I am going to move this side. So what I have, R1 OH X R2 OH. So now this is the plane I am going to consider. मैं मान के चल रहा हूं ना, both the OH group are in the same plane. अगर मैं उस तरह से लिखूं तो इसमें कैसे रिप्रेजेंट कर सकता हूं? इस मॉलिक्यूल को मैं दूसरा लिखने का तरीका क्या है? Now I can write this as R1 R2 and both OH I can write it like that. So इस मॉलिक्यूल को दूसरा तरीके से ऐसे भी मैं लिख सकता हूं, ठीक है? Why? Because if I look from this side now, I can clearly see R1 and R2 are on the right hand side. So it means they are coming towards us, and this is the plane I am considering now. Simply मैंने क्या किया, इसको दूसरे फॉर्म के अंदर लिख दिया है. अब now you can clearly see R1 and R2 are both coming out of the plane. Simply अब इसका रिएक्शन जब इससे होगा, सवाल ये है, now the question is where the phenyl group prefers to stay. It prefers to stay at the equatorial position, and these reactions are happening under the thermodynamic control. Similarly, when you have 1, 2, 3 anti-diol, when you carry out the reaction with benzaldehyde under acidic condition, basically what you are forming is benzalidine acetal. Here also आपकी चॉइस वही है, इसको भी आप इस तरह से ऐसे कन्वर्ट करके देख सकते हैं. So this is the arrangement that we are going to form. So based on the value, for example यहां पर हमारे जो कपलिंग कांस्टेंट हमारी वैल्यूज है, based on these values we can clearly determine what is actually forming, क्योंकि बहुत ज्यादा डिस्टिंक्ट वैल्यू होती है. Now एक एग्जांपल यहां जो उन्होंने कंसीडर किया है, they have considered this example where they have carried out the reduction to give you the ester where both hydrogens are cis to each other, ठीक है? And when they carry out the hydrolysis of ester to acid, this is the product that they get. What they have been able to show that it is this one which is the product that is formed in this reaction. वो कैसे? क्योंकि यहां जब आपको इसका रिडक्शन कर रहे हो, there is a possibility that these hydrogen they can be cis or they can be trans. उनको ये नहीं पता, but when they carry out the hydrolysis, there is a possibility those two products can form. अब ये दोनों के दोनों hydrogen when they are trans to each other, this has a coupling constant of 6. And when they are cis to each other, this has a coupling constant 3.5 hertz. और जैसे मैंने आपको बताया, this 3JHH means this is 3 bond away. This is 1, this is 2, this is 3. So it means these two hydrogens are 3 bonds away. So that is how it can be represented. So this is exactly what they found. They found that this has a value 3.5 hertz, and this can only happen when both the hydrogens are cis to each other. So this is how we can utilize the knowledge of heterocyclic chemistry and to come up with the exact stereochemistry that we are. Now we are going to look at how to determine the stereochemistry when the coupling constant is of no help. Let us suppose एक example ले लेते हैं. Here they have discussed this particular compound, ठीक है? And what they have found कि जो coupling constant between this hydrogen is 11 hertz. So this clearly reflects that दोनों के दोनों hydrogen they are trans to each other. So अगर हम इसका Newman conformation करें तो this is the conformation, that is the preferred conformation. This is the preferred conformation based on the coupling constant that values that we have कि दोनों के दोनों हाइड्रोजन क्या है, ट्रांस है एक दूसरे के. नाउ अगर if I carry out the elimination, ठीक है, what we have is then bromo group here and H. So basically what I am carrying out is the elimination to form the olefin here. लेकिन जब मैं olefin अगर बनाऊंगा, there are two options that I can either form a Z, I can either form an E, ठीक है, there are two options. But here the hydrogen it just cannot interact with कोई दूसरा हाइड्रोजन है ही नहीं. So how do we know whether we have Z or we E? ठीक है, किसी के साथ कपल नहीं कर सकता वो. So we cannot have any splitting pattern to understand whether we are going to get cis or trans. क्या है, ठीक है? In such conditions, what do we use is NOE. It is nuclear Overhauser effect. And इसको in short भी कहते हैं कि through space coupling, where two atoms, दो हाइड्रोजन जो होते हैं, they couple through space, not through atom. It is not through bond. मतलब जैसे under normal condition के अंदर what do we do? हम हमेशा जब साथ में होते हैं, we say that these two hydrogens are coupling to each other because they are missional. Here it is not through bond coupling, it is through space coupling. It means उनका स्पेटियली मॉलिक्यूल ऐसे अरेंज है कि दो एटम एक दूसरे के नजदीक आ रहे हैं. सो किस तरह से NO is different from the normal NMR. एक normal NMR जब हम सैंपल का रन करते हैं, बेसिकली what do? We irradiate the sample with the same frequency. हम उसके साथ सारे एटम को सेम फ्रीक्वेंसी पे रेडिएट करते हैं टू ऑब्जर्व द स्पेक्ट्रम, हमको जो भी मिलता है. लेकिन इन द केस ऑफ NOE इट वर्क्स ऑन द प्रिंसिपल की certain atoms are irradiated selectively. मतलब आपने एक पर्टिकुलर हाइड्रोजन को या एक पर्टिकुलर फंक्शनल ग्रुप को आपने इरेडिएट किया सिलेक्टिवली. जब आप उसको इरेडिएट करेंगे सिलेक्टिवली, वी वांट टू ऑब्जर्व कि क्या उसके रेडिएशन से बाकी जो नियर बाय एटम्स हैं या हाइड्रोजन्स हैं उनकी इंटेंसिटी कम हो रही है या ज्यादा हो रही है या अनचेंज हो रही है. ठीक है, कम तो नहीं होगी. whether there is any change in the intensity of nearby hydrogen atoms. So based on that we can interpret कौन से हाइड्रोजन एटम उस पर्टिकुलर ग्रुप के नजदीक है, whether they are cis or they are trans, or what could be the stereochemistry. So this is exactly the concept that was applied here. ठीक है, वो देखते हैं कैसे. एक और चीज जो बात होती है हमारी NO इंटरेक्शन के बीच में, मतलब आपका जैसे जैसे दो एटम के बीच में डिस्टेंस बढ़ेगा वैसे वैसे NOE का इंपैक्ट घटेगा और ये बहुत इट डिक्रीजेस रैपिडली. फॉर एग्जांपल द डिग्री ऑफ एनहांसमेंट इज इनवर्सली प्रोपोर्शनल टू 1/r/6 वेयर r आपका क्या है, दिस डिस्टेंस बिटवीन टू प्रोटॉन्स. लेट अस सपोज कि समझ लीजिए ये वाला हाइड्रोजन जो है और ये वाला हाइड्रोजन, इनके बीच में जो डिस्टेंस है इन दोनों को हमने r से कर दिया. अगर आप दो एटम के बीच में डिस्टेंस यू इंक्रीज बाय 2 टाइम्स, ठीक है, जैसे कि अगर दोनों के बीच में पहले वो 2 था, ठीक है, 2 सेंटीमीटर था, नाउ यू हैव इंक्रीज्ड इट बाय 4 सेंटीमीटर. दिस इज आर्बिट्ररी नंबर. ठीक है, ऐसा दिमाग में सोच लेना कि 2 सेंटीमीटर होता है, 1 सेंटीमीटर होता है. मैं एक रैंडम नंबर थ्रो कर रहा हूं यहां पे जस्ट टू मेक यू अंडरस्टैंड. इफ द डिस्टेंस बिटवीन टू एटम्स इज ट्वाइस, तो वी कैन क्लियरली इंपैक्ट कि NOE जो है ना वो डिक्रीजेस बाय 64 टाइम्स. कैसे, आपको 2 को आप 6 बार कर लीजिए, 2 2 2 2 1 2 3 4 5 6. So this becomes 64. So if the distance between the atoms becomes twice, then the intensity of NOE becomes 1/64 times. So इसका इफेक्ट बहुत जल्दी डाई डाउन होता है. So basically हम स्पेक्ट्रम में what do we do? NOE स्पेक्ट्रम अगर नटशेल में कोई आपसे पूछे तो क्या है? This is what it is. NOE क्या is basically an enhanced spectrum minus unenhanced. So what do? We run a normal sample. एक normal sample को run करते हैं. And then we run a sample in which certain hydrogens are irradiated selectively just to see the impact. और हम क्या करते हैं, दोनों को subtract कर देते हैं, enhanced NMR versus unenhanced. As a result of which, obviously हमको थोड़े बहुत changes नजर आएंगे. ठीक है, as a result of which those small changes are good enough to reflect what is the stereochemistry or sorry which two atoms are near each other, how they are related to each other through space, not through bond. ठीक है, whenever we talk about NOE, it's always through space coupling. For example, in this particular case, what did they observe? When they irradiated these 4 protons, जो नाइट्रोजन के साथ में these 4 protons को जब उन्होंने irradiate किया, what they observed that the intensity of this hydrogen it increases. ठीक है, इसकी इंटेंसिटी बढ़ गई. सो व्हाट डज दिस क्लियरली रिफ्लेक्ट? ठीक है, इट क्लियरली रिफ्लेक्ट द स्टीरियोकेमिस्ट्री ऑफ मॉलिक्यूल हैज टू बी E. इट मींस व्हेन दिस एलिमिनेशन इज टेकिंग प्लेस, इट इज दिस olefin that is forming, it is not this olefin. क्योंकि यहां पर इस केस में क्या है, the hydrogen is far away. ठीक है, by increasing the intensity of these hydrogen, it has no impact on this particular hydrogenic intensity because this is not close to these hydrogen. So it is through space coupling between this hydrogen and these hydrogen that is happening in this particular case. So this is how on the basis of NOE we can determine the stereochemistry in a lot of cases. ठीक है, उसके अलावा एक और एग्जांपल हमारा क्या है, ठीक है, और अगर हम इसके अंदर देखें भी तो 1 2 3 4 5 दोनों के दोनों हाइड्रोजन और ये वाला हाइड्रोजन, these are 5 bond aways. So 5 bond away तो हमको वैसे भी कपलिंग नजर नहीं आती. So that is the reason why in this case NOE can be very very useful. Now let's look at this particular example. Suppose we carry out the reduction of the carbonyl. So here you can have the hydride attacking from the top or attacking from the bottom. So what did they observe when they irradiated this hydrogen? They observed the intensity of this increased. So this clearly reflects that both the hydrogen they are next to each other. So this hydrogen has to be cis. अब इस केस के अंदर a lot of students might be confused or questioning. Here what I said that it is through space coupling and usually a lot of both the hydrogen atoms are at least 2 3 4 bonds away. Whereas here these two hydrogens are next to each other. Here guys, let's just look at this kind of system that we are dealing with. Here what we have is a 6-membered ring which is fused with 3-membered ring. So this is a highly strained system. मतलब इस सिस्टम में बिल्कुल भी फ्लेक्सिबिलिटी नहीं है. So what they might be seeing कि जब उनको when they got this particular product, maybe the coupling constant of this hydrogen, it might be coupling with this hydrogen, it might be coupling with these two hydrogen, and you are not getting a definite coupling constant values. So that is the reason why you had to rely on the NOE to give you the result. ठीक है? When these hydrogen is and this hydrogen are trans to each other, you do not see any coupling. ठीक है? ऐसे केस के अंदर there is no enhancement अगर आपका नहीं हो सकता उस केस में. So that is the reason why the stereochemistry is cis. दोनों की stereochemistry cis इसीलिए है. Why? Because when you irradiate this hydrogen, the intensity of this one goes up, and this can only happen when they are next to each other. So here it is more to do with this kind of system that we are dealing with rather than how far these two atoms are. And sometimes this coupling constants can be very, very massive. You cannot have the definite values. So that is when NOE can be really, really. So here we are going to talk about the heteroatoms in the ring having axial and equatorial lone pair of electrons. Suppose what we have is a diethyne. Diethyne is this is how we draw. अगर हम इसका chain conformation, if we draw this, then we can clearly see on the sulfur, but we have 2 lone pair of electrons. So one of them can be axial, this is equatorial. Similarly, the other one, this is axial, and this is equatorial. Similarly, in the case of dioxane as well, one of them is axial, one is equatorial, this is axial, this is equatorial. And in the case of piperidine, you can have this hydrogen which is axial in nature. Okay? And these lone pair of electrons, they do play a big role in a lot of reactions. For example, just say we are going to talk about if I have this 6-membered tetrahydropyron, ठीक है? If I draw the chain conformation of this one, ये इसके अंदर इंपॉर्टेंट हमारा क्या है? We can clearly see यहाँ पर तो दोनों के दोनों मिथाइल ग्रुप आ गए. It is this lone pair of electron and this carbon-carbon bond. ठीक है? These two are anti-periplanar to each other. इसका इंपॉर्टेंट रोल क्यों है? Why the overlap of this carbon, this lone pair of electron and this carbon-carbon bond is, why is it important? It is important when we talk about reactions like acetal hydrolysis, when some of the groups are leaving and these lone pair of electron can donate into the carbon-carbon or carbon-oxygen sigma star orbitals, so that they really assist certain reactions. जैसे अगर ये एग्जांपल देख लेते हैं, सपोज इफ वी हैव दिस पर्टिकुलर मॉलिक्यूल एंड वी कैरी आउट द एसिटल हाइड्रोलिसिस, हियर व्हाट वी हैव इज एन ORI. What we would assume that these lone pair of electrons, they are coming here and it is being kicked out, and then water attacks and it gives rise to the formation of acetal product. But logically, if we think about it, is this feasible? This is not feasible at all. What is the reason why? Because we can clearly see that these lone pair of electron here on oxygen, this is axial, this is equatorial, they have no way, they just cannot donate into the carbon oxygen sigma star orbitals. It's just not available. ठीक है? And moreover, this leaving group, it is at equatorial position. From whatever I have taught you so far, जैसे मैंने बताया भी हुआ है कि whenever the donation होगा, अगर होना है तो this has to be at equatorial position so that this can donate into the sigma star orbitals and the good leaving group can leave. For that, the leaving group has to be axial in nature. ठीक है? ये तो वन पॉइंट हो गया. उसके बाद लेट अस कम टू द अदर पॉइंट. अगर इफ वी आर हैविंग such type of an oxenium ion intermediate, can you imagine how strained this is, having a double bond on this quaternary center? This is impossibly strained. So the molecule or the reaction just cannot go via this intermediate. If this reaction is taking place, if this hydrolysis is taking place, there has to be some other mechanism, but it is not via this oxonium ion intermediate. इसके उलट, let us just look at another example. Here they have considered another example where when they are carrying out the hydrolysis, it is very, very fast. And here what we can see, instead of ORI group and at the equatorial, here it is at the axial position. Now it can easily donate into the anti-bonding orbital of carbon oxygen, and this being a good leaving group, this leaves. So here the rate of hydrolysis is 10 to 10 times faster than this case. So you could be asked a question in the exam, out of these two, which one has the faster rate of hydrolysis and what is the reason? What is the reason behind that? So this is something that you have to explain there. Okay. So next in the chapter they have talked about that there are certain substituents in saturated heterocycles they prefer to be at the axial position. And the effect that we are going to talk about, the anomeric effect. Usually anomeric word in itself is जब भी आपका 6 मेंबर्ड हेटेरोसाइकिल के अंदर, फॉर एग्जांपल मोस्टली हम यहाँ पर हम बात कर रहे होते हैं टेट्राहाइड्रोपायरन डेरिवेटिव्स की. सो इसकी जो अल्फा पोजीशन के ऊपर, दिस इज द कार्बन, दिस इज कॉल्ड द एनोमेरिक कार्बन. ओके, सो दिस इज कॉल्ड द एनोमेरिक कार्बन. और इसके ऊपर जो भी सब्स्टिट्यूएंट होता है उसको हम क्या कहते हैं, एनोमेरिक सब्स्टिट्यूएंट. इसके ऊपर यहाँ पर जो भी होता है, जैसे फॉर एग्जांपल यहाँ पर वी आर डिस्कसिंग द एग्जांपल ऑफ द ग्लूकोज. ग्लूकोज हमको पता है यूजुअली it doesn't exist in the cyclic form. It's usually less than 1%. So what it does, when you have this OH, it attacks the aldehyde. So this OH, newly formed OH, it can either be axial or it can be equatorial. So specifically in the case of the glucose, what you have is a 64% exists in the form where OH is at equatorial position. So here what we can say, it is this substituent which is at equatorial position, or this anomeric substituent which is at the equatorial position. Whereas in this case, this OH is at axial position and this exists 35%. Now, this anomeric effect is very very important, क्योंकि अब तक हमने क्या पढ़ा है, what we have studied so far is in the 6-membered system. This is what we have studied. All the substituents, they prefer to be at the equatorial position because of the steric reasons. So what happens in the case of THP? THP में ऐसा क्या खास होता है कि the substituent which is at the anomeric position prefers to stay at the equal axial position. There has to be some reason. This is exactly what we are going to study here. So let us suppose a simple example. Usually here this is an example of tetrahydropyran derivative, or although this can also be treated as an example of sugar derivative. Here what we have, what we can see at alpha position, what we have is a methoxy derivative. This is a methoxy substituent which is at the equatorial position. So this is only 33%, whereas this substituent when it is in axial position, this exists in 67%. Here we are talking about the equilibrium. So equilibrium, under equilibrium, it is this substituent at axial position which is major as compared to the equatorial position. Similarly, अगर आप इसके acetate derivative की बात करेंगे, so this acetate prefers to be at the axial, and this equilibrium lies far to the right hand side when the substituent is at axial position. Here it is at the equatorial position. So if I have to define the anomeric effect, I can say that in a tetrahydropyran system, here what we have is a tetrahydropyran system, and if I have substituent at position number 2, okay, if I have a substituent at position number 2, this substituent prefers to be at the axial position rather than the equatorial position, because this substitution at axial position is more stable than the substitution at the equatorial position. Now we are going to look at the reason. What is the exact reason how this particular molecule acquired stability? ये substituent यहाँ होने के बाद इसके बाद stability कहाँ से आती है? And usually when we talk about this system, it is this substituent, it is usually the electronegative atom. ये बहुत important है, electronegative substituents. So when I say electronegative substituents, it could be halogens. It could be halogens like chloro, fluoro, anything, or it could be ऑक्सीजन. ऑक्सीजन के डेरिवेटिव आपके OAC हो सकता है, OMe हो सकता है, या O-ethyl हो सकता है, और it could be नाइट्रोजन के डेरिवेटिव, it could be N-ethyl, it could be N-methyl. You understand? So those kind of derivative. Here we are talking about the electronegative substituent, means oxygen, nitrogen, or these halogens. ठीक है? So this is something that is very very important. Now we are going to understand the reason what brings stability to such. So now we are going to understand the reason for that. Before we touch upon the reason, now let us look at a very similar example. हमको पता है कि the amides are usually less reactive and more stable than the ketones. और उसका reason क्या होता है? उसका reason, if we see that the lone pair of electrons that are on oxygen, they undergo conjugation with the carbonyl group. So as a result of which, what is happening? This carbon-oxygen bond, this becoming weak. लेकिन in reality, what is happening? So the lone pair of electrons that are there in the or p orbitals of nitrogens, they are parallel. Okay, they are parallel to this carbon-oxygen sigma star orbitals. That is the reason why the overlap is much better, and because these carbon-oxygen pi star, this is carbon-oxygen pi star orbitals, they are low lying, मतलब उनकी energy lower होती है. That is the reason why that overlap is pretty firm. ठीक है? That is the reason why, because of this overlap, they undergo conjugation, एज अ रिजल्ट ऑफ दिस कॉन्जुगेशन हमको पता है दिस कार्बन ऑक्सीजन बॉन्ड, जो यहां पर इट इज अ ट्रू डबल बॉन्ड, बट हियर दिस बिहेव्स मोर लाइक अ सिंगल बॉन्ड. सो इसकी बॉन्ड एनर्जी जो होती है दैट इज इन बिटवीन द डबल बॉन्ड एंड द सिंगल बॉन्ड. ठीक है, एज अ रिजल्ट ऑफ दिस ओवरलैप इट बिकम्स weakened. So what is the primary condition? Primary condition क्या होती है कि अगर आपके लोन पेयर ऑफ इलेक्ट्रॉन्स है, यहां पर जो नाइट्रोजन के ऊपर लोन पेयर ऑफ इलेक्ट्रॉन्स है वो, और जो भी उसके नेक्स्ट सब्स्टिट्यूएंट है, ठीक है, जो भी उसके नेक्स्ट सब्स्टिट्यूएंट है उसके पाई स्टार ऑर्बिटल्स या उसके सिग्मा स्टार ऑर्बिटल्स, क्योंकि यहां हम कार्बन ऑक्सीजन डबल बॉन्ड की बात कर रहे हैं, दैट इज व्हाई वी आर टॉकिंग अबाउट द पाई स्टार ऑर्बिटल्स. अगर यहां पर एक सिग्मा बॉन्ड होता तो हम सिग्मा स्टार ऑर्बिटल्स की बात करते, ठीक है, वो इस केस के अंदर होगा हमारा. नाउ when you have this tetrahydropyran substituents, ठीक है, और यहां पर आपके what you have is this carbon chlorine bond. What happens in this case? This is exactly what happens. Now this lone pair of electron on oxygens, they are axial or they are equatorial. They can, and on this carbon chlorine bond, so ये जो कार्बन ऑक्सीजन बॉन्ड के जो सिग्मा स्टार ऑर्बिटल्स हैं, ठीक है, दिस इज द सिग्मा स्टार ऑर्बिटल्स, ये क्या, दे बोथ आर पैरेलल टू ईच अदर, एज अ रिजल्ट ऑफ विच दे कैन इजीली डोनेट हियर. अगर वो यहां पर इजीली डोनेट कर रहे हैं, सो दिस इज वेरी सिमिलर टू दैट. सो व्हाट इज हैपनिंग एज अ रिजल्ट ऑफ दिस डोनेशन, दिस कार्बन क्लोरीन बॉन्ड इट वीकन्स. ठीक है, ये कार्बन क्लोरीन बॉन्ड वीकन्स हो जाता है, और ये ओवरलैप की वजह से, बिकॉज इट इज डोनेटिंग इट्स इलेक्ट्रॉन इनटू द सिग्मा स्टार ऑर्बिटल्स, it is providing stability to that particular molecule because there is a kind of a conjugation that is happening. Whereas अगर हम equatorial position की बात करें, when this carbon chlorine or this chlorine is at the equatorial position, here you have an axial electrons and here what you have is a lone pair of electron of the equatorial position. Here this carbon chlorine sigma star orbitals, they are not properly aligned. मतलब इस लोन पेयर के साथ भी ये अलाइन नहीं है प्रॉपर, इसके साथ भी प्रॉपर अलाइनमेंट नहीं है, बिकॉज दे आर नॉट पैरेलल टू ईच अदर. एज अ रिजल्ट ऑफ विच नन ऑफ दीज, मतलब इन दोनों में से कोई भी लोन पेयर ऑफ इलेक्ट्रॉन दे कैन नॉट डोनेट इनटू दिस सिग्मा स्टार ऑर्बिटल्स, मतलब इन केस ऑफ द इक्वेटोरियल. दैट इज द रीजन व्हाई दिस सब्स्टिट्यूएंट इट प्रेफर्स टू बी एट द एक्सियल पोजीशन. और उसके लिए सबसे इंपॉर्टेंट फैक्टर क्या होता है कि व्हेन यू हैव दीज heteroatoms, or I should say the electronegative substituents, that is the exact word. These electronegative substituents, they have low link, ठीक है, they have low link or low energy, you can say low link carbon x sigma star orbital. मतलब क्योंकि इनकी एनर्जी लो होती है, that is the reason why such overlap or such donation of electrons is favorable. Now so what is happening, this is exactly what I've shown. When these lone pair of electron comes, this behaves more like a leaving group. So in it is a kind of an interaction that is happening, where what you have is this, as a result of lone pair of electron, this carbon chlorine bond is becoming weakened and its length increasing. So that is why it prefers to stay at the equatorial position. It's a very, very important example which could be asked in the exam. Now we are going to look at yet another important example of anomeric effect, especially in the case of these spiroketals. Now these spiroketals are a very important structural features in various insect hormones. और इनको बनाने का one of the best methods to make them is, first what you have to take basically is diols and having a ketone. अगर आप इस कंपाउंड को as soon as you expose this under to acidic condition, ठीक है, what you get is the spiroketalization that takes place. उसका मैकेनिज्म pretty straightforward है, उसका मैकेनिज्म. सो फर्स्ट स्टेप के अंदर आपका क्या हो रहा है कि this undergoes protonation, ठीक है, आपका यहां पर इसका protonation हुआ. So what happens, it attacks here, this comes. So what you get is like this, something of on these lines, OH, ठीक है. उसके बाद सेकंड आपका क्या हो रहा है, दोबारा से इसका जब आपका प्रोटोनेशन होता है, देन दिस इट कम्स बैक एंड दिस लीव्स. सो ये जब लीव कर जाता है तो व्हाट यू फॉर्म इज दिस एन ऑक्सीनियम आयन, और ऑक्सीनियम आयन आपका जैसे ही बना OH इस पे अटैक किया, सो व्हाट यू गेट इज अ स्पायरोकेटल. सो दिस इज अ वेरी, वेरी इंपॉर्टेंट, दिस इज समथिंग दैट यू शुड नो, यू शुड डेफिनेटली नो दिस, दैट हाउ टू मेक दैट. एग्जाम के अंदर यू कुड बी गिवन सच कंपाउंड्स, या फिर यू कुड बी गिवन लाइक OTBS or OTBS here and you could be shown that TBF, ठीक है. So you should know as soon as such diols are formed, they immediately spiroketalize, ठीक है. under acidic condition. It could be BF3 ethylate as well, and it could be under gold catalyzed. मैंने इसके ऊपर वीडियो भी बनाई हुई है, so you should know that. And यहाँ पर तो it is 6,6, it could be 6,5 as well. It could be 6,5, something like this. ठीक है, it could be like this as well, depending upon the carbon length के बारे में. Now इसको एक्सपोज किया, दिस इज व्हाट यू फॉर्म. सो व्हाट आर द वेरियस पॉसिबल कन्फॉर्मर्स फॉर सच कंपाउंड्स. ठीक है, देयर आर 3 पॉसिबल कन्फॉर्मर. अगर मैं इसको ड्रॉ करूं, व्हाट आर द 3 पॉसिबल कन्फॉर्मर? 3 पॉसिबल कन्फॉर्मर व्हाट यू कैन हैव इज one at axial and one at equatorial. So this is at axial, this is at equatorial, or both of them can be at the equatorial position, or both of them can be at axial position. So this is a very, very important example. Why I say this? Because they can ask you, or they can show you what are the possible, which is the best possible conformer for this particular molecule to exist in. So you should know it is this particular conformer. उसका reason क्या है? Because only in this conformer, what you have is this lone pair of electron and oxygen. They are axial, and this one is equatorial. This is axial, and this one is equatorial. Only these lone pair of electrons which are axial, they donate into this carbon oxygen sigma star orbital, and this one donate also into this carbon oxygen sigma star orbital. So what is happening here is a double anomeric effect. ठीक है, not only one axial lone pair of electrons is donating this electron into the carbon oxygen sigma star orbital, it is 2 that is happening. Whereas these equatorial lone pair of electrons, they are not properly aligned to donate into the carbon oxygen sigma star orbital. So it is this particular conformer, when the both substituents are axial to each other, they are more stable because of the double anomeric effect. So this is a very, very important example that you should know. Now we are going to look at similar examples where something very similar on the lines of anomeric that effect that is happening, which is being discussed in the book chapter. Now we are going to look at a very similar effect in other types of compound. ठीक है, अभी तक तो हमने बात करी थी, we have talked about the THP derivative having a electronegative substituent at position number 2, which prefers to be at the axial position, which is called anomeric effect. This is what we have talked about. But this effect exists in other type of compound. And what is the key criteria? What is the most important criteria that you should look for? This is the key requirement. Heteroatom with lone pair of like oxygen, nitrogen, sulfur, whenever they are lying next to a low lying anti-bonding orbital. मतलब जब भी आपका heteroatom होगा which is lying next to a low lying anti-bonding orbitals, हमेशा ये फैक्ट आपको तब ऑब्जर्व होगा. जैसे फॉर एग्जाम्पल here, ठीक है, देख, और ये दोनों these two are very important examples. I'm telling you, these two are very important examples, and there's no doubt that they will be asked in the exam, in some of the entrance exam, and they will definitely be asked. So we must understand what is happening here. In this case, this is one of the preferred conformation for this compound when we are talking about the cyclic structure. Here this R is an axial position. जब ये R axial position पे हो जाता है, तो what is happening? These lone pair of electrons, they are equatorial at position. ठीक है, and here what we have is this oxygen, और this carbon oxygen के जो हमारे sigma star orbitals हैं, this one, ये और ये, they both are parallel to each other. As a result of which these lone pair of electrons, they donate into this carbon oxygen sigma star orbital. क्योंकि दोनों के दोनों exactly parallel हैं. This is the exact thing that we are talking about here. Because carbon oxygen क्या है कि इसकी वजह से, because of the strong electronegativity of this oxygen, these sigma star इसकी एनर्जी क्या हो जाती है, लेस हो जाती है. This is the reason why this donation becomes preferred. ठीक है, so remember this is the preferred conformation. Now here let's talk about this particular compound. अब तक हमने क्या पढ़ा है? This is obviously a cyclohexane का डेरिवेटिव है. अगर यहाँ पे मैं नाइट्रोजन को कार्बन से रिप्लेस कर दूं, cyclohexane का डेरिवेटिव है. और यहां पर what we are seeing, this is the preferred conformation. This is the preferred conformation. और remember, इस पे क्वेश्चन इसलिए आएगा, why this is preferred conformation? दो यहां पर tertiary butyl group equatorial है, the other one is at axial position. From what we have studied so far, we say that this just cannot be the case. Why would a bulky group be at the axial position? We will understand that. ठीक है, और अगर हम दूसरी तरह से देखें तो तीनों के तीनों इक्वेटोरियल भी हो सकते थे. They would have been equatorial, but what happens कि दो हमारे इक्वेटोरियल है और एक हमारा एक्सियल है. ऐसा भी तो हो सकता था कि हमारा एक एक्सियल है सॉरी एक इक्वेटोरियल है हमारा और दो के दो एक्सियल हैं, लेकिन when two of them are equatorial, one of them is axial, it kind of brings stability to the molecule. उसका रीजन हम देखते हैं what is happening. So the lone pair of electron on this nitrogen, what they are equatorial. और ये हमारा जो कार्बन नाइट्रोजन है, this कार्बन नाइट्रोजन के जो हमारे सिग्मा स्टार ऑर्बिटल्स हैं, they are here. इस कार्बन के नाइट्रोजन के सिग्मा स्टार ऑर्बिटल्स are here. So what is happening? There is a double donation of electron. मतलब आपके जो ये lone pair of electrons, they are undergoing डबल कॉन्जुगेशन विद कार्बन नाइट्रोजन सिग्मा स्टार ऑर्बिटल्स, इस वाले कार्बन नाइट्रोजन के साथ भी, इस वाले के साथ भी. एज अ रिजल्ट ऑफ विच इट प्रेफर्स टू स्टे इन दिस पर्टिकुलर कॉन्फॉर्मेशन. ठीक है, दैट इज द रीजन व्हाई यू हैव टू ट्रिशेबल ग्रुप एट द इक्वेटोरियल पोजीशन एंड वन एट द एक्सियल पोजीशन. जब ये एक्सियल पे आएगा, आपके ये जो लोन पेयर ऑफ इलेक्ट्रॉन है जो कि इक्वेटोरियल पे है, अब तक हमने क्या पढ़ा है कि उसको एक्सियल ही होना चाहिए, लेकिन जब ये हमारी इक्वेटोरियल पे होते हैं, व्हाट इज हैपनिंग, ये जो कार्बन नाइट्रोजन के जो पाई हमारे सिग्मा स्टार ऑर्बिटल्स हैं, इसके क्या है, दोनों के दोनों एंटी पेरिप्लेनर हैं. और अगर आपको ये टर्म समझ नहीं आ रहे, एंटी पेरिप्लेनर, सिन क्लीनर, सिन पेरिप्लेनर, आई हैव मेड अ वीडियो ऑन दैट व्हिच इज कॉल्ड द टॉर्जन एंगल, आई थिंक टॉर्जन स्टेन, आई थिंक कुछ तो ऐसा वीडियो मैंने बनाया, उसके अंदर आप देख सकते हो. I think this is to be deleted. Okay, so that is the reason why you must remember this is the preferred conformation. Now, I'll come back to one of the very basic question. हमको पता है कि मिथाइल क्लोराइड, it is a very reactive electrophile. जबकि जब हम बात करते हैं डाइक्लोरोमीथेन, it is unreactive and it is used as a solvent. This is kind of a baffling if you think about, क्योंकि हम usually क्या करते हैं, मिथाइलाइड एंड मिथाइल क्लोराइड को as a source of मिथाइल यूज करते हैं, जबकि यहां पर बड़ी एक्स्ट्रा क्लोरो, उसकी वजह से तो इसकी इलेक्ट्रोफिलिसिटी और ज्यादा बढ़ जानी चाहिए, लेकिन दिस इज नॉट व्हाट इज हैपनिंग. सो क्या रीजन हो सकता है? इज इट द स्टीयरिंग? बिकॉज मिथाइल क्लोराइड का स्ट्रक्चर देखें तो व्हाट यू हैव इज अ हाइड्रोजन, इट इज बीन रिप्लेस्ड बाय अ chloro. This is what is happening. So there has to be a sterics that are associated with the chloro, which is causing this reaction, this dichloromethane to be unreactive. लेकिन ऐसा भी केस नहीं था. उसका रीजन क्या है कि अगर ऐसा केस है तो when this hydrogen is replaced by मिथाइल और प्रोपाइल, बट दे हैव सीन देयर, वो ज्यादा रिएक्टिव है डीसीएम से भी. मतलब हमारा इथाइल क्लोराइड और प्रोपाइल क्लोराइड भी हमारा डीसीएम से ज्यादा रिएक्टिव है. सो स्टीयरिक इसका रीजन नहीं हो सकता. इट कैन नॉट बी स्टीयरिक. देयर हैज टू बी सम अदर रीजन. सो द अदर रीजन इज दैट इन द केस ऑफ डाइक्लोरोमीथेन व्हाट एग्जिस्ट्स इज व्हाट यू कॉल एज अ परमानेंट एनोमेरिक इफेक्ट. परमानेंट एनोमेरिक इफेक्ट आपका क्या होता है? हमें पता है कि क्लोरो के पास देर आर 3 लोन पेयर ऑफ इलेक्ट्रॉन्स. ठीक है, हर एक क्लोरो के पास 3 लोन पेयर ऑफ इलेक्ट्रॉन है. सो इन द ग्राउंड स्टेट ऑफ द मॉलिक्यूल हमेशा एक ऐसा कॉन्फॉर्मर होता ही है जिसके अंदर दिस लोन पेयर ऑफ इलेक्ट्रॉन ऑन दिस क्लोरीन, दे आर डोनेटिंग इनटू दिस कार्बन क्लोरीन सिग्मा स्टार ऑर्बिटल्स. मतलब दोनों के दोनों क्या कर रहे हैं यहां पर, इसके कार्बन क्लोरीन के सिग्मा स्टार ऑर्बिटल्स के अंदर आपके डोनेट कर रहे हैं इलेक्ट्रॉन. दैट इज द रीजन व्हाई in its ground state it is very stable. That is the reason why it is pretty unreactive. ठीक है, आपका ये वाला भी आपका जब ग्राउंड स्टेट के अंदर obviously they are just moving around, so there is always a conformer. एक ऐसा conformer होगा ही होगा जिसके अंदर ये इसके अंदर डोनेट कर रहे हैं. That is the reason why it is unreactive. ठीक है, so this is a very important factor and it should remember, because at times in interviews this is one of the question that is usually asked to the students ki what do you think is the reason why this is unreactive, and I mean you should remember the basic concept. It is because of the permanent anomeric effect that exists in the dichloromethane. Okay, so here we are talking about the chemistry of the acetals. So the tagline is acetal exhibits stereoelectronic control over conformation. It's a pretty heavy line. इसको हम simplify करने की कोशिश करते हैं. So this is the acetal that we are talking about. Okay, अगर हमारा एसिटल इस पर्टिकुलर कॉन्फॉर्मेशन में रहेगा, वी कैन क्लियरली सी दीज लोन पेयर ऑफ इलेक्ट्रॉन्स. इसको मैंने आई हैव शोन इट लाइक दैट फॉर क्लैरिटी दैट दे आर कमिंग आउट ऑफ द प्लेन, दे आर गोइंग आउट ऑफ द प्लेन. क्योंकि अगर हम इसका स्ट्रक्चर ड्रॉ करें, अगर मैं इससे ऐसे ड्रॉ करूं, सो आई कुड हैव आल्सो शोन इट लाइक दैट, क्योंकि हमें पता है ऑक्सीजन के ऊपर देयर आर 2 लोन पेयर ऑफ इलेक्ट्रॉन. ठीक है, जस्ट टू बी ऑन द सेफर साइड आई हैव शोन लाइक दैट. सो दिस इज द एक्सटेंडेड कॉन्फॉर्मर. बट व्हाट इज द इशू विद दिस पर्टिकुलर कॉन्फॉर्मर कि none of these lone pair of electrons they are donating into the carbon oxygen sigma star orbitals. ठीक है, इसका ये प्रॉब्लम है. So what is the best scenario that can happen? अब इसको आपको सिंपली इसको रोटेट करके इसको दूसरी फॉर्म में लिखना है. So this is the best possible scenario जहां पे हम देख सकते हैं कि both methyl group are empty to each other and these lone pair of electrons now they can donate into this carbon oxygen sigma star orbital. So for such acetal this is the most preferred conformation and this is called the gouache conformation or the synclinal conformation. This is a very important example. Again, you could be given variety of choices and you could be asked for this particular acetal which is the most stable conformer. So you should know it is the gouache conformer which is also synclinal which helps these. अब आपका क्या हो चुका है कि these lone pair of electron now they are in the same plane और आपके जो इस कार्बन ऑक्सीजन के जैसे अगर मैं बात करूं कि इसके एंटी ऑर्बिटल इसके कार्बन ऑक्सीजन के लो लेइंग एंटी बॉन्डिंग ऑर्बिटल से उस पर डोनेट कर सकता है. सिमिलरली ये कार्बन ऑक्सीजन का ये होगा, ये यहां पर आपका डोनेट कर रहा है, यहां पे डोनेट कर रहा है जिसकी वजह से इसको स्टेबलाइज हो रहा है. ठीक है. Now if we shift our attention to a simple ester, हमको पता है कि there are two factors usually जो contribute करते हैं. हम हमेशा क्या करते हैं, what do we do? We simply write it like that. So this is very similar to the case of the amides. So what is happening? It is the donation of lone pair of electrons from oxygen into this carbon oxygen sigma star orbital. ठीक है, कार्बन ऑक्सीजन के sigma pi star orbital सॉरी उसके अंदर आपका डोनेशन हो रहा है. बट देयर इज अ सेकंड फैक्टर व्हिच वी आल्सो मस्ट कंसीडर. अगर हम देखें फॉर दिस पर्टिकुलर एस्टर दिस एल्काइल ग्रुप इट कैन बी सिस. अगर मैं इस कार्बन ऑक्सीजन बॉन्ड को कंसीडर करूं, ठीक है, इसके अराउंड दिस कैन बी सिस और इस कार्बन ऑक्सीजन बॉन्ड के अराउंड दिस सब्स्टिट्यूएंट कैन बी ट्रांस. जस्ट समझने के लिए आउट ऑफ दीज टू व्हिच वन इज मोर प्रेफर्ड. ये तो प्राइमरी फैक्टर हो गया जिसकी वजह से इट इज गेटिंग स्टेबलाइज्ड. एंड व्हाट अबाउट द सेकेंडरी फैक्टर व्हेन द सब्स्टिट्यूएंट इज cis when the substituent is, so what is happening, ये जो कार्बन ऑक्सीजन का what is this is the carbon oxygen, this is pi star orbital. ठीक है, this is the carbon oxygen sigma star orbital. So what is happening, these lone pair of electron on oxygen they are parallel to the carbon oxygen sigma star orbital, as a result of which this is the additional stability, this provides additional stability. Where in this case अगर हम इस केस की बात करें जब substituent हमारा क्या होता है ट्रांस होता है, what is happening, these lone pair of electrons and they are away, they are far away from each other, so no additional stabilization is possible in this particular case. जबकि इस केस के अंदर that is what is happening. So apart from the donation of lone pair of electron into the pi star orbitals, there is also a donation when substituent is cis. So you could be asked a variety of questions that in the case of the ester whether this R prefers to be the cis or it could prefers to be the trans. So you should know why it prefers to be the cis, because in that case these lone pair of electrons and this carbon oxygen sigma star orbitals are anti-periplanar to each other. That is the reason as a result of which there is an additional donation of additional stabilization as a result of the donation of electrons. So that is what is happening, and here it is a gouache conformation which brings the extra stability. Okay, so these are the things that you should know. Now we are going to talk about the ring closing reactions for the synthesis of various heterocyclics. That is how easy or how difficult it is to form the ring. So this has been explained in the book in the form of the table where they have described two type of reactions. So here what is happening, here is an amine and bromo. So it is the SN2 substitution in presence of a base, and here what we have is a diethyl malonate derivative. So here what you do is generate a carbanion and replace the bromo to form the ring. So here what they've shown is the ring size and relative rate. Here the relative is related to the formation of six-membered ring. So if we consider the six-membered formation as 1, okay, which is faster, इसके रिलेटिव के अंदर बाकी रिंग साइज को कंपेयर किया गया है. सो वी कैन क्लियरली सी इन दिस केस द रिलेटिव रेट फॉर 3 membered is 0.06 and for 4 membered it is way less, and for 5 membered it is higher. Actually in both the cases the formation of 5 membered ring is more than the 6 membered ring, and as we go higher in the size the rate of the reaction further decreases. ठीक है, तो अगर हम एक जनरल रफ गाइड करें regarding the rate of the reaction from the data. So this is the data that they actually got. So now we have to somehow explain this data logically. So if we look at the data, we have seen that the fastest is the 5-membered ring and then slowest are the 8 to 10-membered ring. क्योंकि जैसे हमारा ring size बढ़ता है, as the size of the ring increases, there are other type of interactions like transannular interactions, they come into play as well. So that is the reason why forming bigger size rings is not possible. But what is so interesting to see actually is this formation of 3-membered ring and formation of 4-membered ring. From what we know about the 3-membered rings or small size rings, we know the ring strain is very high. Ring strain is very high in, let's say, 3-membered rings, right? Ring strain की वजह से what is also high? The transition state. Transition state is of the reaction is pretty high. As a result of which the activation energy is high. So it means that the forming such rings is not easy at all. And as the size of the ring increases, the activation energy decreases, as a result of which making rings much more easier. ठीक है? लेकिन अगर ऐसा होता, if that is the case, then it's difficult to explain why forming 3-membered ring is easier as compared to 4 or even 7-membered ring. So ring strain is not the only reason. ठीक है? Ring strain है, but उसके अलावा there has to be some other reasons that we need to explain. So this is exactly what has been explained now, where we are going to talk about the equation, that is Gibbs free energy equation, delta G is equal to delta H minus T delta S. We are going to consider how that entire equation is important when we are talking about the relative rate of the reaction and ease of formation of reaction, and also why apart from ring strain there are other factors that are important as well. This is exactly what we are going to see now. So as I said, if ring strain is the only factor, then the rate for 3-membered ring should have been the lowest, and for 6-membered ring it should have been the maximum, right? However, what we saw, the order was 5 into 6 into 3 and then next. So what are the other factors that are contributing to it? So here what we are considering, this is delta G, which is the Gibbs free energy. So what we can say, it's an activation barrier, right? Now it is made up of two terms, which is delta H and delta S. This is the enthalpy and this is the entropy. Now this is the energy that we require, that is required to bring two atoms together. For example, when you are carrying out a reaction, that is the example that we talked about, right? What is the amount of energy that is required to make sure that these atoms are very near each other? Means these two are near each other in order for reaction to take place. Obviously, when these two atoms they are coming close to each other, they are experiencing all kind of strain and they are experiencing different kind of repulsive forces. So the energy that is required to bring them closer against all the kind of other forces that are acting upon the molecule. So it is that delta H factor which is important. Apart from that, the second factor which is very important is the delta S. Now the delta H, it is the how easily you can form a very ordered transition state. We clearly know, for example, for this particular molecule, the molecule is randomly orienting in various directions, but there is one particular conformation in which the molecule comes into exactly the right conformation for the reaction to take place. So it is this factor which takes us into the consideration. मतलब हमारा एंट्रोपी एक तरह से बताता है किस तरह से मॉलिक्यूल एक प्रॉपर ऑर्डर्ड फैशन में बन रहा है, ठीक है, in order for the reaction to take place, because we know a particular molecule can have n number of conformation. So how easily it can reach that ordered transition state. So it is this factor that takes that into the consideration. So activation barrier is made up of these two terms, ठीक है, and based upon the ring size, one or the other factor dominates, as a result of which we see the kind of relative rates that we see, where we have seen that the 5-membered ring is more than 6 and 6 is more than 3 and 3 is more than 7, then comes 4 and then 8 to 10, whatever rate that we saw previously. Now this is exactly what we are going to see, what is happening, all those two factors, how they are contributing it. Now we are going to look at that. Okay, so now now let's just talk about the ring size 3 or 4. Okay, so what are the factors that predominate in the case of 3 and 4? We know this is the general equation and it is made up of two terms, that is delta H and delta S, and this is the activation barrier, right? So in the case of when you are going to form 3-member or 4-member ring, for such molecules there are very few conformation possible. So इसका मतलब क्या है कि for such molecules to reach an ordered state, they can very easily reach that ordered state. As a result of it, इसका मतलब क्या है कि इनकी जो delta S value है, that is going to be very, very small. Why? Because it can reach the reactive conformation, and that reactive conformation is like, let us suppose if there are 4 conformations that are possible. Out of those 4, it is just the one that is the reactive. So the number of choices are pretty less. So here the dominating factor is delta S because it has a less value. Whereas, what is the big problem in such cases? It is the ring stain. That is the delta S, which is large in case of 3-member ring. Why? Because the ring stain is very, very high. So you need a lot of energy to bring these two reacting molecules together against all the repulsive forces that are happening here. That is the reason why for 3 and 4, delta H is large and delta S is small. अगर हम बात करते हैं for 5 to 7 member rings की, exactly उसका reverse होता है. Why? Let us suppose यहाँ पे मैं 6-member ring की बात, 7-member की बात कर रहे हैं, that is what we are forming. How many conformations are possible? This molecule could be linear, it could be linear as well, right? So that is one of the conformation it can have. It can be linear, it can have n number of conformations, and out of those n number of conformations, there is one reactive conformation, which is this one, which might be reacting. इसका clearly मतलब क्या है? इसका मतलब है here the delta S is going to be large. इसका मतलब entropy is going to be more contributing factor, क्योंकि इस पूरे मॉलिक्यूल को उस रिएक्टिव फॉर्म में लाने के लिए इसको काफी ज्यादा मेहनत करनी पड़ेगी. However, अगर हम बात करें कि साइज ऑफ द रिंग बड़ा है तो इसका मतलब क्या है कि स्टेन नहीं है. सो द वैल्यू ऑफ डेल्टा एस इज गोइंग टू बी लेस. इसका मतलब क्या है कि टू ब्रिंग दीज टू रिएक्टिव एटम्स, मतलब NH2 को कार्बन को पास में लाने के लिए इट डजंट हैव टू कंज्यूम अ लॉट ऑफ एनर्जी, क्योंकि यहां अदर रिपल्सिव फोर्सेस के आपके वो लेस है. बट द प्रॉब्लम इज डेल्टा एस, क्योंकि देयर आर एन नंबर ऑफ possibilities of conformation. Out of this, only one can react. So, depending upon the ring size, one or the other factor dominates. That is the reason why we observe जो हमारा rate of the reaction था, ठीक है, in the case of a 3-membered ring, it's not the slowest. Why? Because it is not only the ring strain that is a factor, it is the entropy. Entropy यहाँ पर favor कर रही है formation के लिए, क्योंकि out of number of conformation, एक मतलब 2 या 3 पॉसिबिलिटीज में से एक आपका रिएक्टिव है, तो एंट्रोपी फेवर कर रही है 3 और 4 मेंबर को, और एंथैल्पी फेवर कर रही है 5, 6, 7 को. इसको एक दूसरी तरीके से देखने का तरीका ये है that these are enthalpy driven processes and these are entropy driven processes. Okay, so now let's jump into the other factors. So here we are going to talk about the example that has been discussed under the tagline thermodynamic control over ring size. So this is a very interesting example. Here what you have taken is the mannitol, right? Mannitol is subjected to the synthesis of, it's a protection that they have done. They have basically done the benzylidine protection. इसके बारे में I have already made a separate video. So this can be done, it's a protection of diols. So what you do is use benzaldehyde under acidic condition, and what it does is basically it is protecting this OH with this one, and it is protecting this with this one. So that is the protection of 1,3-diol. But biggest question is why it is happening like that? Why there is a 1,3-diol protection in this case? And when you treat mannitol with acetone under the same condition, what do you observe is the 1,2-diol protection. So here what you have is a 1,2-diol getting protected as acetonite, and here what you are having is a 1,3-diol getting protected as a benzylidine. Okay, so what is the reason for that? The reason is specifically in the conformation that it acquires. For example, when the 1,3-diol protection takes place in this particular case, the molecule acquires an all-equatorial conformation. If you draw the chair structure of this particular compound, so that is what you are going to have, where you can see all the groups pH, OH, and this pH, they all acquire the equatorial position. So it is the preferred conformation for in the case of the benzylidine. Lekin in the acetonite, let us suppose if when you treat with the acetone, what it will happen? Let us suppose this is the reaction with the acetone under acidic condition. Why it is not giving the same compound? Uska reason kya hai? If I draw the chair conformer of similar to the benzylidine, you can clearly see these methyl groups. They are occupying the axial position. यहाँ पर भी axial position. You draw any conformation, any chair conformation, it is inevitably these methyl groups are going to be at the axial position. So this process is not thermodynamically favored in this case. ठीक है? In the case of acetone, thermodynamics does not favor the 1,3-diol protection. Here it is favored. Why? Because it acquires the all equatorial conformation. That is the reason why mannitol के साथ जब आप reaction करते हैं, it gives the 1-diol. ठीक है? थोड़ा सा आप कंफ्यूज हो रहे होंगे इसमें कैसे ड्रॉ किया है. What you can clearly see कि दो चीजें बहुत, there are many ways to write the acetonite protection. या तो what you can do, you can just move this into the upper side. So this is a simple transformation you can do. If you carry out this transformation and then if you show like this one, इसका मैं acetonite protection अगर दिखाऊं acetone के साथ, ठीक है? So this is what you are going to have. Rather than these two are trans, तो इसका मतलब क्या है कि इन दोनों को प्लेन में दिखाया तो these are going to be trans. ठीक है? इसका acetonite protection हो गया, इसका acetonite protection हो गया. Apart from that, they could have also shown you, इस तरह से भी आपको दिखा सकते थे. In lot of places, you can also have like this one. Suppose you could have also have like O. You could have like O. They could have shown you like this one. काफी बार होता है इस तरह से दिखाया जाता है, and the student gets confused, right? You should not be confused. इस तरह से, और आपका क्या है ये? Oxygen इस तरह से, ठीक है? So this acetonite protection is shown like this one, arrow, ठीक है? Don't get confused in that particular, उस तरह से आपको दिखाया जाएगा, ठीक है? So we have clearly seen how thermodynamics can be very, very important when it comes to the ring size, and this is a very important example, ठीक है? Now we are going to talk about the Thorpe-Ingold effect. So here it says the combating entropy. So now what we have seen in the as far as the smaller ring size are concerned, that ring size 3 or 4, मतलब छोटे ring size में entropy आपकी favorable होती है because the number of conformations are few and it easily reaches the required ordered transition state for the reaction to take place. But what about the higher size ring? ठीक है? What about the higher size rings? Their delta S is problematic. So how we can combat that? So the Thorpe-Ingold effect is about that. So let us just consider क्या हो रहा है. Suppose what we are doing for this 3-membered again, then we are going to go into the higher size. We are going to look at the other examples. So when you are basically generating a alkoxide anion and replacing the chloro acid to substitution to form the epoxide, the relative rate is 1. But when you introduce 2 methyl groups and you are carrying out the same reaction, what has been observed? The epoxide formation. Look at the rate of the reaction. It is 4 into 10 to the power 4. That is amazing. That is amazing. And how do you explain that? एक तरह से हमने क्या किया है? There are 2 methyl group which must cause the lot of sterics. ठीक है? Sterics should come into play. जिसकी वजह से the rate of the reaction should be less. But here we are observing reverse. So in a way, adding the substituents into the molecule makes the reaction go faster. This is what we are seeing. When Thorpe and Ingold, they tried the same effect on the other substrates. Here on the 4-membered ring, they did the same reaction. Rate was 4, and when they introduced 2 methyl groups, you can clearly see it increased by 400 times. So that is an amazing effect. So we must look further into it. So here what you have, you are trying to make the pyrrolidine. Here the relative rate is 1. When you introduce 2 methyl groups, it increased 2 times. And when you introduce these 2 methyl group at carbon next to it, then the rate is 160 times. अगर इससे मैं compare करूँ, the rate has increased 160 times. So there has to be a reason. और हम इसको कैसे explain कर सकते हैं, ठीक है? So in a way, Thorpe-Ingold effect basically tells once you put substituents on the ring, it increases the rate or equilibrium constant for the ring forming reaction. So whenever you are forming a ring, whenever you are forming a ring and whenever you are introducing substituents onto the ring, मतलब अगर आप जब भी एक ring form कर रहे हैं, especially the heterocyclic ring, and when you are introducing substituents, मतलब यहाँ पर आपने substituents डाले, वो क्या कर रहा है? It is increasing the rate of the reaction or equilibrium constant for the ring formation and reaction, and that is what is called Thorpe-Ingold effect. And we are going to look at what is the reason why, how this effect is making reactions go faster, why the sterics are not coming into play. Okay, let's look at that. Just to highlight what are the reasons why having substituents increase the rate of the reaction or the equilibrium constant. Here we can just consider one more example. So when you are basically cyclizing the diacid into the anhydride, you can clearly see when you introduce 2-methyl group, the rate jumps from 1 to 14. And when you have these tetramethyl group, the rate directly jumps from 14 to 24,000. So having 4-methyl substitution, the rate constant increases by 24,000 times. So what are the reasons? So for this particular case, actually there are two reasons. So what we are doing is basically, the first is the angle and the second is the entropy. So we are going to look at both these. So what is happening when you have the diacid? The dihedral angle between them is 110. Okay? And when you introduce these two substituents, so what is happening? It is very similar to VS-EPR theory, where you talk about the bond pair repulsion. Having these two substituents, what they want, they are repelling these substituents, as a result of which they are forcing these two diacids to be close to each other. So without substituents, they were that far. As a result of the substituent, they moved slightly closer to each other. So if we clearly see, the dihedral angle here is 106 degrees. So although there is a change of only 4 degrees, but that change is good enough for the cyclization to take place. ठीक है, थोड़ा सा change ही at times in reaction is a very important factor in bringing about the reaction into the forward direction. So this is exactly what is happening in the cases of the diacid. Now, अगर हम बात करें other cases that we have discussed previously, for example here हमने पढ़ा था, पहले हमने क्या पढ़ा था, especially for the 5-membered or 6-membered case, 5-membered, 6-membered, 7-membered, we can clearly see there are number of conformations that are possible, as a result of which the entropy is very, very high. The entropy is very high, and the energy required to get to the desired transition state makes the entropy very, very negative. So the value of entropy in higher size rings is very negative. The negative value is pretty negative to get to the required transition state. ठीक है? What happens when we introduce the substituents? It is again the same thing that is happening. It is a repulsion. Now, once you have these two substituents, अब ये substituents क्या कर रहे हैं? They are repelling the groups. ये इन groups को यहाँ पर क्या कर रहे हैं? They are repelling. As a result of this repulsion, what they are doing? They are limiting the flexibilities. मतलब यहां पर जिस तरह से molecule can have various conformation, here the flexibility of the molecule has been limited. इसकी वजह से if we compare these two cases, the delta S value to reach the desired transition state is going to be less negative, right, as compared to this case. If this is going to be less negative, it means the delta G is going to be more negative. ठीक है? Why? Because what we have is a delta G is equal to delta H T डेल्टा एस. अगर ये हमारा लेस नेगेटिव होगा तो ये हमारा क्या होगा? ज्यादा नेगेटिव होगा. एंड इफ डेल्टा एस इज गोइंग टू बी more negative, it means that the activation barrier is low. It means the reaction is going to form faster under the thermodynamic control. So that is the reason why in the case when we introduce the substituents on the ring, first they have an impact on the angle between the two substituents, मतलब जो उनके बीच में substituent के बीच में, especially in the case of the when you are talking about the diacid, when such cyclizations are taking place. Okay, so here we can talk about these angles, and these angles. ठीक है? The second is the, because of the repulsion between the substituent, the flexibility is limited, as a result of which the delta is not that negative, which is the case when it doesn't have the substituents. So that was about the Thorpe-Ingold effect and how it can be used to combat the entropy. So now we are going to talk about the Baldwin rules. And especially in the case of the saturated heterocyclic, when we are carrying out a cyclization, then there has to be some degrees of rules which the reaction must follow in order for such cyclizations to take place. Okay, so Baldwin, he came up with these guidelines. Remember, these are guidelines. These are not to say that the reaction is not going to work. So based on the rules that he devised, you can in a way predict that what type of cyclizations are favored and what type of cyclization are disfavored. So okay, so when I say that it is favored, so in a way what Baldwin predicts that based on the kinetics the reaction should work. इसका मतलब ये है कि according to the Baldwin's and the rules that he suggests, the reaction should work kinetically. However, we will see a number of exceptions in which the reactions tend to go against the Baldwin rules, and those reactions are controlled by the thermodynamic factors. Okay? So he gave guidelines to say whether the reaction is favored or the reaction is disfavored. For example, if we are carrying out the electronization of the acid and alcohol under acidic condition, or we are carrying out such cyclization of alcohol onto the alkynes. Basically, in a way we can say this is kind of a naming system. For example, जैसे कि depending upon the name, if I just say 3-exotet, what this would clearly give me an impression that what I am forming is a 3-membered ring, and exo means the attacking taking place on the inside, and tet means electrophile, the kind of electrophile I am dealing with. What is the hybridization of that electrophile? So it can give me a lot of information about the exact type of cyclization that is taking place. So this is exactly how such cyclization reactions are classified. So it's a very simple system. देखने की कोशिश करेंगे. तो first thing is always the ring size. जब भी पहला number होता है, for example here it is the ring size. So this number 3, it means 3-membered, 5 means 5-membered, 6 means 6-membered. So depending upon the first digit that you will see, it is always means the kind of ring size that you are making. मतलब पहला जो सबसे रूल है, या पहला डिजिट होता है, आप देखते हैं किस तरह का आपका रिंग साइज बन रहा है. दूसरा, जो आपका बॉन्ड आपका ब्रेक हो रहा है, the bond that is breaking either on the inside, जैसे कि यहां पर आप क्या कर रहे हो, this carbon and bromine bond, ठीक है, lone pair of nitrogen, they are attacking on the inside. अगर if it is attacking on the inside, we call it an exo. If it is attacking on the outside, we call it endo. For example, अगर मान लीजिए ये नाइट्रोजन ब्रोमो पे अटैक करता, अगर ये इस कार्बन ब्रोमीन, ठीक है, इसके आउटसाइड अटैक करता, we would have called it endo. जो तीसरी चीज है, it is the nature of the electrophile that we are dealing with. For example, जैसे यहां पर this is carbon bromo. Okay, so this is the kind of alkyl bromide that we are dealing with. Here यहां पर आपका nature of electrophile है a carbonyl. Here the nature electrophile is your alkyne. So this is the simple system that Baldwin decides. The first is ring size. The second is the kind, the way the attack is taking place. Is it attacking on the inside, that is exo, or the outside, which is endo? The third is the nature of electrophile that we are dealing with. अगर आपकी जो electrophile की stereochemistry, not the stereochemistry, sorry, अगर electrophile की आपकी hybridization sp है, then you can call it dig, which means diagonal, right? अगर वो sp2 है, we call it trigonal, short में उसका नाम है trig. If we are dealing with sp3, it is tetrahedral, so we call it tet. So these are the three terminologies that we use. अब इसका example देख लेते हैं, बहुत simple है ये. For example, यहाँ पर what we are forming is a 3-membered ring. So we are going to name it. पहले जो हमारा न्यूक्लियोफाइल है उसको हमेशा नंबर 1 देंगे. Always remember the first numbering is going to be the nucleophile which is attacking. So this is 1, 2, 3. So this is the electrophile. So we are going to number as 3. So the kind of what sort of a ring that we are forming? We are forming a 3-membered ring. So this is what we are forming. So पहला नंबर आपका आ गया 3. Now this is attacking is taking place on the inside. Since it is taking place on the inside, so it means it is exo. So 3-exo. Now what about the hybridization? इस कार्बन की हमारी hybridization क्या है? इस कार्बन की hybridization क्या है हमारी? It is sp3. So it means it is tetrahedral. Now we are going to write the tet. So this is means 3-exotet. अब ये मुझको क्या information दे रहा है? What kind of information I can draw from this one? If someone tells me 3-exotet cyclization, I can clearly understand that they are talking about a cyclization reaction in which I am forming a 3-membered ring, and the attack the nucleophile attacked on the inside, and the new electrophile on which it attacked, its stereochemistry was the tetrahedral. So it means here I'm talking about the SN2 type of substitution reactions. ठीक है, दूसरा example देख लेते हैं. So here what we are carrying out the electronization. Very similarly, this is getting protonated. Again, सबसे पहला नंबर इसको देंगे nucleophile को. So this is 1, 2, 3, 4, 5. So one carbon is attacking on the 5. So what type of ring system that we are forming? We are forming 5-membered ring system. Now, since it is attacking on the inside, it is exo. अगर ये यहाँ पर इस पर अटैक करता तो it would have been endo. And this, what about the hybridization of this particular carbon? इसकी hybridization क्या है आपकी? Trigonal है आपकी. So it is going to be trig. So this is going to become 5-exo trig. Now let us come to the other example. सबसे पहले again nucleophile को पहले नंबरिंग 1, 2, 3, 4, 5, 6. Now there are two possibility. आपका यहाँ पर भी अटैक कर सकता था, आपका यहाँ पर भी अटैक कर सकता था. But here in this case, it is attacking on the outside. सबसे पहले तो it is forming 6-membered ring. So number of the ring size. ठीक है. Now there are two sides that can attack. It could have attacked here as well. अब इस केस के अंदर इस अटैक को हम क्या बोलते हैं? इसको हम एक्सो बोलते हैं. यहाँ पर since it is attacking on the outside, we call it the endo. ठीक है. That is what it is says. And what about the stereochemistry of this part? Sorry, I am saying stereochemistry. It is hybridization. What about the hybridization of this carbon? It is sp. Since it is diagonal, so it is dig. So that is a very simplistic approach to name such cyclization reaction, which was given by the Baldwin. And based upon that, I'm going to actually show you a chart afterwards that what type of cyclizations are favored and what type of cyclizations are not favored. Now we are going to discuss the certain cyclization reactions that have been discussed in the book chapter. Okay. So later I'm going to show you the chart that has been given in the book, which I think it's pretty easy to memorize, so student can memorize. So it will give you a general idea about the kind of cyclization that are favored and that are not favored. But here we are going to discuss what has been discussed in the Clayden chapter. So they say that all the exotet cyclization and all exotrig cyclization are favored. So when I think about exotet, so here they have not talked about the ring size. So it means that for any ring size, such cyclizations are favored. And exotet, if I think of exotet, I can clearly mean that whatever nucleophile, it is attacking on the inside. And what about the hybridization of the electrophile? It is tetrahedral. It is sp2, and here it is here it is sp3, and here it is sp2. So those are favored by the Baldwin's rule. So we are going to look at the first of all exotet cyclization. What is happening? So let us suppose in such system. So okay, this is what it means, right? You have a nucleophile, and then what you have the hybridization here is what you have is a sp3, right? So this is nothing but exotet cyclization. So what is happening? The lone pair of electrons on Y, which is like a nucleophile, it could be an amine or it could be an alkoxide, right? So this undergoes overlap with this carbon halogen CX sigma star orbitals. This is something that we have already understood. So as a result of this overlap, such cyclizations are favored. Similarly, when we talk about the exotrig, so instead of carbon oxygen, what we have is a carbon CX double bond. So this can be carbonyl as well, right? So here as well, the lone pair of electron on Y, what they undergo overlap with the carbon X double bond pi star orbital. अब यहाँ पर pi star orbital के साथ उनका overlap होता है, as a result of which such cyclizations are also favored. Now, if we talk about the 5 or 6 endotet, so अगर मैं 5 या 6 मतलब here they are talking about the 5 endo, मतलब आपकी अगर 5-membered ring बन रही है, endo means if the attack is taking place on the outside. And if I'm talking about what about the tetrahedral, and the hybridization of that carbon has to be sp3. Such are disfavored. They are not disfavored. So here we are going to talk about such example, which at times can give you an impression that 6 endotet or 5 endotet cyclization is happening, but in reality that is not the case. So this is a very good example. So here what we have is a substrate. And when you expose this to a base, we know that this acidic proton is what you have. So the base is going to abstract this proton. It will generate a carbene at this position. So what they observe when they when they expose this compound to the base, the product they isolated was having a methyl group at this position. Now, यहां पर वो तभी हो सकता है कि अगर ये कार्बेनियन आपका मिथाइल पे अटैक करे, इसका मतलब समथिंग ऑन दीज लाइंस। सो अगर हम यहां बाल्डविन रूल अप्लाई करें तो बाल्डविन रूल हमेशा मैं सबसे पहले बोलता हूं द फर्स्ट थिंग इज व्हाट इज द न्यूक्लियोफाइल, न्यूक्लियोफाइल इज द कार्बेनियन एंड what is the ring size? This is 1 2 3 4 5 6. Although here you are not forming a ring, but it is going via 6-member transition state. So this nucleophile is attacking the methyl and they are 6 away, that is it is at the 6th position away. So in a way it is the ring size is 6. Although this is not a cyclization, but we can this is the kind of transition state via which it is going. So it is attacking the methyl group, and it is the 6-member ring, and since the attack is taking place on the outside, that is why it is endo, and since the hybridization of this is sp3, it is going to be tetra. Now the question is it really the 6-endo tet? We have said that such are disfavored. Then how such reaction is taking place? Now Schenwasser, he did some crossover experiments to find out this is not what is happening. The reaction is not intramolecular, right? So here यहाँ पर अगर हम देखें तो if I just give you this data, you might be inclined to believe that the reaction is taking place via the intramolecular cyclization, ठीक है, intramolecular abstraction of the methyl group. That is how the reaction is taking place. जबकि in reality this reaction is intermolecular in nature, which was proved by the crossover experiment. We are going to look at क्या एक्सक्लूजन ने किया था, क्या प्रोडक्ट मिले, जिनके बेसिस पे he concluded that it is not this which is taking place and such cyclization according to the Baldwin rules are disfavored. So basically what Schenwasser did, he carried out the crossover experiments. So the crossover experiments are very, very important experiments whenever you have to in a way prove that the reaction is taking place intramolecularly or intermolecularly. So what he basically did, he prepared this substrate instead of having an OC methyl group. What he took is like CD3, and here also what he did like a CD3. Basically इन्होंने क्या किया, deuteriation किया. So in the crossover experiment, what you do basically, you take like a deuteriation at certain position जहां आपको लगता है कि the exchange might be taking place, and what you take is an original molecule. Then you are trying to see whether the original molecule क्या वैसे का वैसा intact रहता है या उस पर भी कुछ ना कुछ deuteriation हो रहा है कि नहीं हो रहा है. This is something that you see what are the kind of कितना आपका deuteriation retain हो रहा है, कितना आपका consume हो रहा है, उसका distribution pattern क्या है. So this is how you deduce the exact nature of the mechanism that is happening in the reaction. So उन्होंने क्या किया, सच मॉलिक्यूल लिया, ठीक है, उन्होंने इसके साथ दूसरा सबस्ट्रेट भी लिया, ठीक है. So in the reaction what they observed that as soon as this carbanion is generated, instead of, पहले हमने क्या बोला था कि इस तरह का कुछ हो रहा होगा, instead of abstracting this one, it does not. What it does, it abstracts the methyl from the other atom. So what it does is basically rather than आपका क्या होता है कि आपका यहां पर rather than CD3 what you get is a CH3. तो उन्होंने एक्सपेरिमेंट्स में क्या करा, अगर ये रिएक्शन, अगर जब आप रिएक्शन में ऐसे करते हैं कि इसका भी आपका कार्बेनियन जनरेट हो रहा होगा ऑब्वियसली, ठीक है, दोनों का जनरेट होता है, एंड व्हाट इट डज बेसिकली इट आल्सो abstract this deuteriation from the other molecule. So this was the other product that is observed. Although they have not shown this product in the book, lekin this is also one of the product that they observe, because it's not only the one product that you see the other product as well. So based on the formations of such products, they were able to determine that such reactions are intramolecular in nature rather than the intermolecular. Okay, such crossover experiments are very, very useful in making sure what is happening. So this is exactly what he did. So next we're going to talk about the 3, 4 and 5 endo-trig cyclization. So these cyclizations are disfavored as we can see. And what about 6, 7 endo-trig? These cyclizations are favored. So we are going to look at, जैसे ही when I talk about 3, 4, 5 endo, I can clearly think, so what we are forming is 3-member ring, and endo, it means the attack is taking place from the outside, and trig clearly means that the hybridization of that particular carbon or that particular nucleophile, electrophile is going to be sp2. So such are disfavored. So now we are going to look at the example, or ये example has been asked in this year's NET exam. So we can see यहाँ पर what you have is an amine and here you have is a conjugated ester. So it can attack, the amine can attack in a conjugate manner to give the desired pyrrolidine. But this does not happen. This 5-endo trick does not happen. 5-endo trick कैसे? हमेशा मैंने बोला था, first is the nucleophilic center and the first is the nucleophilic center जहां से attack हो रहा है, वहां से हम numbering करते हैं. So the first is always the ring size. So this is 1, 2, 3, 4, 5. So we are forming 5 ring size. Endo means outside. यहाँ attack होता है, it would have been exo. This is endo. Trig. Since this, the hybridization of this is sp2. So this is trigonal. So that is why trig. इस तरह से this is not favored. सबसे बड़ा रीजन क्या है कि why this is so bad? Why 5-endo trig is so bad? उससे पहले जनरली देख लेते हैं कि with amines they are very good at undergoing conjugate addition with unsaturated ester. मतलब it's not as if कि amine conjugate addition नहीं हो सकते. It does. In fact, they are very good at doing that. But this cyclization is not favored. This is bad. Why is it so? अगर हम इसका अलाइनमेंट देखने की कोशिश करें कि किसी भी कॉन्फर्मेशन के अंदर या तो क्या होता है कि अलाइनमेंट इज प्रीटी बैड और द न्यूक्लियोफिलिक सेंटर, दैट इज द लोन पेयर ऑफ इलेक्ट्रॉन दीज नाइट्रोजन्स, दे आर टू फार अवे फ्रॉम द pi star orbitals of this double bond. जैसे कि in this particular arrangement the alignment is pretty bad. So the lone pair of electrons, they are not properly aligned. So you can see that both of them are perpendicular to each other. So that is the reason why this lone pair of electrons, these pi star orbitals of carbon-carbon double bond are not aligned properly. Let us suppose अगर ये दोनों के दोनों properly aligned भी हो जाए, that is lone pair of electrons are parallel to the pi star orbital. In this case, we can clearly see they are too far away. So that is the reason why the 5-endo trig are pretty bad. That is the reason why this does not take place. अब हम इसका exception भी देखेंगे. Rather than ये बोलने के what actually happens, then this one is going to attack the carbonyl. The conjugate addition के बदले what happens is 5-exo trig. So that is favored जो हमने पहले देखा हुआ है. Again देख लेते हैं ring size कौन सा बन रहा है. 1, 2, 3, 4, 5. So we are forming 5 and exo मतलब attack is taking place on the inside. अगर यहाँ होता तो it would have been outside. So it is exo, इस कार्बन की हमारी hybridization is sp2 which is trigonal, so it is trig. And we know 5 exo trigs are favored. So that is the reason why instead of getting this, you get this desired product in this case. So इसका हमने reason देख लिया है. Now we are going to look at the example of 6-endo trig. क्योंकि हमने बोला कि 6 or 7-endo trigs they are favored. We are going to look at the example. So here what we have done, we have taken this. हमें मॉलिक्यूल को देख के पता चल रहा है कि it must be undergoing conjugate addition to form such type of a ring. यहाँ पर the question that could be asked could be stereochemistry. इसको भी हम डील करेंगे. We are going to look at that. So what you have is a base. This is the active hydrogen. So base is going to abstract that. So what you generate is a carbanium. Carbanium आपका क्या कर रहा है? O negative is coming back and this carbon is attacking in a conjugate manner. So this cyclization is 6-endo trig. Again, ring size 6. Endo मतलब it is attacking this carbon. अगर यहाँ अटैक करता तो it would have been exo. Exo पे होता तो 5 हो जाता है यहाँ पे, ठीक है, which is not favored. So it is 6-endo trig क्योंकि इसकी क्या है हमारी hybridization is sp2. So this is trigonal. Now one of the questions जो कि students को often can be confusing that why the stereochemistry of this hydrogen and this ester is cis, why they are coming out of the plane. यहाँ पर this is the relative stereochemistry they are talking about. Again, I always say that अगर इसकी जगह they would have shown this, it would have been perfectly fine. Because here we are going to show the relative stereochemistry. Because starting material there is no stereochemistry that is present. ठीक है, यहाँ पे so we are showing the relative stereochemistry of both these functional groups. So इसको समझना बहुत आसान तरीका है. Now let us imagine this hydrogen is coming out of the plane. ठीक है, if this hydrogen is coming out of the plane, then it means this particular group is going behind the plane. Okay. Now अब आपका देख रहे हैं कि what is happening, this carbon, ठीक है, once this negative charge from oxygen comes back, it is this carbon which is attacking the chain in a conjugate manner. और ये जो हमारा पूरी की पूरी chain है, this entire chain, this is going behind the plane. ठीक है, if this is going behind the plane, so there is no option that this carbon has to attack this chain from below the plane. अगर ये चेन यहां से बिलो द प्लेन अटैक करेगी तो मतलब जो नया कार्बन कार्बन बॉन्ड बनेगा दैट इज गोइंग टू फॉर्म फ्रॉम बिलो द प्लेन. अगर वो बिलो द प्लेन होगा सो दिस फंक्शन इज गोइंग टू कम आउट ऑफ द प्लेन. सो दैट इज हाउ वी एक्सप्लेन द स्टीरियोकेमिस्ट्री दैट इज ऑब्जर्व्ड इन दिस केस. So now we are going to look at the exceptions of this particular case, जहां पर हम देखेंगे how instead of NH2 if we have an SS, that is thiol group, how we end up getting the desired product. That is an exception to 3, 4, 5, 5 endo trig that we have called disfavored. लेकिन उस केसेस में होता है. As I have said that Baldwin rules are just the guidelines that goes to show whether reaction is feasible or not. It is based on the kinetics. But if the thermodynamics really favor a reaction, then they do go at times. So here we are going to talk about the two examples which are the exceptions to the Baldwin rule. So as we said previously that if such 5 endo trig, they cannot take place, but here they can take place and such reactions are under thermodynamic control. As I said, the Baldwin rules are just the guidelines and it just goes to show the kinetic favorability. But if the thermodynamics allow, the reaction may proceed. For example, here what we are doing is basically carrying out the acetal protection of ketone with 1,2-ethane-diol. So under acidic condition, this is how it is proceeding to give the intermediate. Now, this particular intermediate then undergoes 5 endo trigs. So here again 1, 2, 3, 4, 5 lone pair of electrons, they attack, it opens. अगर हम देखें under normal circumstances, but we have said that this is not favored, but such protections are under thermodynamic control. We can see that reversible. Okay, this clearly shows that these reactions are under thermodynamic control. और अब ये बात कर लेते हैं जो कि इस बार नेट के एग्जाम में आया था, where what you have is a thiol, you treat with the base. So base से आप क्या करेंगे, जब treat करेंगे, it is going to abstract this proton to form the thiolate carbanion. This thiolate carbanion then attacks this conjugated ester in a conjugate manner. ठीक है, conjugate addition हुआ. So here what we are getting is 5 endo trig. Again 1, 2, 3, 4, 5. 5 is the ring size. Endo is attack since this is taking place on the outside, not on the inside, and trig is the hybridization of this one, which is sp2, so it is trigonal. So that is why this is taking place. Now, what could be the reason? Obviously, अगर हो रहा है तो we need to explain. So one of the reasons we can say that the carbon sulfur bond, it is long. So अगर सर एक बॉन्ड लॉन्ग है, कार्बन नाइट्रोजन से कार्बन सल्फर बॉन्ड को कंपेयर करें, हमें पता है कार्बन सल्फर बॉन्ड इज स्लाइटली लॉन्गर. सो इट मींस इट कैन रीच द pi star orbital, empty pi star orbital of this carbon-carbon double bond. Second चीज कर सकती है, we know what sulfur has. Sulfur has these empty 3d orbitals. These empty 3d orbitals, we know that the 3d orbitals are more diffuse. As a result of which, क्या हो रहा होगा? They might be interacting with the pi orbitals of this carbon-carbon double bond. ठीक है? इस interaction की वजह से ये जो नेगेटिव चार्ज है, it can reach the sigma star orbitals of the carbon-carbon double bond. So these are the two reasons to explain this observed phenomena. So अगर हमें in the nutshell, if we have to say, we will say that the tet or trig cyclization are usually exos are better for exo than the endo. जबकि with the diagonal reverse is the true. इसका मतलब whenever the attack is taking place on the diagonal, let us suppose, what does this mean? It means कि अगर आपका इस तरह से है and you have the attack on the endo, so this is much favored. ठीक है, when you have the diag here the जिसके ऊपर इलेक्ट्रोफाइल पे अटैक हो रहा है, that is favored. पर अगर आपका डबल बॉन्ड है या फिर आपका अगर इस तरह का है, उस केस के अंदर अगर अटैक हो रहा है तो आपका एक्सो इज फार बेटर. एक्सो द अटैक इज ऑन द इनसाइड or this is on the outside. So that is what they are trying to say. That's kind of a general statement that you must remember. Now we are going to look at the last part of this one which has been discussed in the book. So they say that all exo-dig cyclizations are favored, जो कि हमने पीछे भी बोला हुआ है. Suppose we have such alkynes in conjugation with the ketone and we have a tertiary alcohol present in the molecule. So they are treating it with the base. So base is going to absolutely abstract this acidic proton to generate the alkoxide carbanion. Now, this alkoxide ion can undergo 5 endo trigs because this is like attacking here. So we can have something like that. This can come back to give you this molecule. Again, 1, 2, 3, 4, 5. So we have the 5-member ring. Exo means attack is taking place on the outside. Dig is the hybridization of this one. So that is what we will get. ये हमने पहले भी देख लिया था. और उसका रीजन क्या है? अगर मैं इसका मॉडल ड्रॉ करने की कोशिश करूं, नॉट द मॉडल, इफ वी ट्राई टू सी कि ऑर्बिटल ओवरलैप कैसे हो रहा है. सो व्हाट वी हैव इज अ लोन पेयर ऑफ इलेक्ट्रॉन्स हियर, और ये जो एल्काइन है, वी नो दैट एल्काइन के ऊपर इट कैन आइदर बी परपेंडिकुलर और इट कैन बी इन द प्लेन. सो दीज वंस, दीज ऑर्बिटल्स, दीज पाई स्टार ऑर्बिटल्स आर दे आर inaccessible. They cannot be accessed because this lone pair of electron के ये क्या है, they are perpendicular. where we have these orbitals, for example this one and these one, these are parallel to the lone pair of electrons on oxygen, as a result of which there is a cyclization is much more favored. So they are accessible, these one which are parallel, and these perpendicular ones are the inaccessible. So that is why such cyclizations are usually favored. And apart from that, 3 and 4 exotics are disfavored and 5 and 7 are favored. ये आपको इनके बारे में थोड़ा बहुत इंफॉर्मेशन होना चाहिए, ऐसा नहीं है कि आपको एक एक चीज पूरी पूरी मेमोराइज करनी है, बट why such cyclizations are favored you should be able to justify it with the explanation. Now so far we have talked about the Baldwin rules when it comes to the ring closing. हमने यहाँ पर रिंग बना रहे हैं. What about the ring opening? Are these rules applicable to the ring opening as well? Yes. Baldwin rules अगर मान लीजिए जो भी हमने अब तक डिस्कस किए हैं, whatever holds true for the ring closing, it holds true for the ring opening. अगर हमने बोला है कि all endo-dic cyclizations are favored for ring closing, so opposite मतलब ring opening के लिए भी यही true है. जो आपका ring closing के लिए true है, that is also true for the ring opening. Just remember this. Let us consider this particular case. So here what we have is a saturated heterocycle. आपने methoxide ion डाला, it abstracts this proton to generate this intermediate. Now what they are doing, they are quenching this intermediate with the deuterated methanol just to see if the ring opening takes place. दो पाथ भी हो सकते हैं. Either this can come back and it can, this carbon-carbon bond can break to give you this ring opening system. This is called the reverse 5 endo trig, which is happening. ठीक है. Again हमको पता है इन जनरल 5 एंडो ट्रिग क्या है, अनफेवरेबल है, जो कि रिंग क्लोजिंग के केस में है. ये हमने पढ़ा है कि रिंग क्लोजिंग में 5 एंडो ट्रिग्स आर अनफेवरेबल. सो रिंग ओपनिंग में भी वो अनफेवरेबल है. सो इंस्टेड क्या होता है कि once this comes, the lone pair of the negative charge comes back, it abstracts the deuterium to give you this compound. So basically what is happening, this hydrogen is getting exchanged with the deuterium and you do not observe any ring opening. इसको हम कैसे जस्टिफाई करेंगे? So अगर हम इसका अगेन इस इंटरमीडिएट का अगर हम मॉलिक्यूलर पिक्चर ड्रॉ करने की कोशिश करें ऑर्बिटल्स का, so we can clearly see कि हमारा ये जो पाई ऑर्बिटल्स है, दिस पाई ऑर्बिटल्स और दिस सिग्मा स्टार, ये कार्बन ऑक्सीजन का सिग्मा स्टार ऑर्बिटल्स, ठीक है, कार्बन ऑक्सीजन का सिग्मा ऑर्बिटल्स, ठीक है, ये वाला और ये वाला, इन दोनों के बीच में दे आर ऑर्थोगोनल टू ईच अदर, एज अ रिजल्ट ऑफ विच दे कैन नॉट इंटरैक्ट. सो दैट इज द रीजन व्हाई सच रिवर्स एंडोट्रिग आर नॉट फेवर्ड. ठीक है, वी कैन लुक एट द चार्ट. इट्स आई थिंक इट्स इजी टू मेक. सो व्हाट यू कैन जस्ट ड्रॉ 3 4 5 6 7. आप ये नंबरिंग 3 बार लिख लो. सिमिलरली इसी नंबरिंग को रिवर्स ऑर्डर में लिख लीजिए और यहां पर यू कैन जस्ट पुट टेट ट्रिग डिग here exo and endo. So what you have to do, basically you have to make a line from here, making sure 7 6 को cross कर रही है here and just make a line here. So anything on this part is disfavored, this is disfavored, this is favored. So इसको पता कैसे लगाना है, इसको इंटरप्रेट कैसे करना है. ठीक है, इसको इंटरप्रेट करना है. 7 endo tet are disfavored, 5 endo tet are disfavored, 5 endo trig are disfavored. At the same time 5 एंडो डाइक आर फेवरेबल. ठीक है, जो भी आपका इस पार्ट में आ रहा है दैट इज फेवरेबल. सिमिलरली इफ यू विल गो टू लाइक 5 एक्सो टेट, इट इज इन द फेवरेबल. सो इट इज प्रीटी इजी एंड प्रीटी यूजफुल. I think if you can memorize it, you will be able to solve many questions. So next we are going to talk about the homotopic groups, enantiotopic groups and diastereotopic groups. इसके बेसिस के ऊपर there are general questions that are asked. Most of the times they were asked in a manner which of these compounds are either what is the relationship between them, or which one of these is homotopic or enantiotopic or diastereotopic. It is pretty easy. Homotopic के केस के अंदर जैसे for example you will have a compounds like these. Let us suppose इसको मैं HA और HB लेवल कर देता हूं. ठीक है, अगर मैं इसको मान लीजिए रोटेट करूं by 180 डिग्रीज. ठीक है, this is 180 डिग्रीज रोटेशन. तो what you have with the HB यहां आ जाएगा, HA यहां आ जाएगा. बट इन रियलिटी अगर मैं इस कंपाउंड को ड्रॉ करूं, what is this? This is like this one. So it is a symmetric compound and that there is no way you can distinguish by any method इस प्रोटॉन को HA को HP से. So such protons are homotopic. ठीक है, इसको that is one way to look at it. दूसरी चीज जो कि मैं हमेशा बोलता हूं कि for two students is, अगर let us suppose if I replace this hydrogen by a functional group, let us suppose I say replace this by a cyano. ठीक है, क्या ये करने से इफ आई कैरी आउट दिस ऑपरेशन डज द कंपाउंड बिकम कायरल, क्या इसके अंदर कायरल बन जाता है, क्या इस कंपाउंड के नेचर में कुछ फर्क आता है? नो. व्हाई? यू हैव दीज टू ग्रुप्स व्हिच आर सेम एंड जस्ट देयर इज जस्ट नो वे. ठीक है, so these two groups are same, so this is not enantiotopic as well, and यहां पर हमारा डायस्टीरियोटोपिक का सवाल ही पैदा नहीं होता. So in such cases such hydrogens or such groups are called the homotopic groups. ठीक है, क्योंकि because there is just no way to distinguish between them. Now in cases के अंदर it is pretty easy. Let us suppose what we have is a two hydrogen, although यहां पर भी we cannot distinguish between these two hydrogens क्योंकि NMR के अंदर भी they are chemically equivalent. But how do I know that this is an enantiotopic? Why? Let us suppose इस केस के अंदर if I replace one of the hydrogens with a functional group, जैसे कि यहां साइनो किया, if I do that, for example pH, let me replace this by a cyano. Now what I have generated is a chiral center. और अगर मैं now if I just rotate this by 180 degrees, what am I going to have? I am going to have is a pair of enantiomer, right? This is what I am going to have. So that is the reason why, since I am going to have this pair of enantiomer, if I carry out a substitution, that is why such compounds are called, or such groups are called. For example, especially these hydrogens are called enantiotopic groups. What about the diastereomer? In most diastereomers के केस में you will already have a chiral center. ठीक है, you already have a chiral center. Let us suppose अगर मैं इस हाइड्रोजन को again, if I replace this hydrogen, either one of them, यहां पर भी या फिर इधर के हाइड्रोजन में भी, कहीं पर भी, if I replace any of the hydrogens by a functional group, of course what I am going to generate is a pair of diastereomers. So that is the reason why these groups are called the diastereomeric groups or diastereomeric protons. So that was pretty much about the chapter 31, and thanks a lot for watching the video. Have a good day.